start.
Okay, good. So, like I said yesterday, this is a simplified daily generation profile of an 8 kilowatt peak PV system. Okay, so if you're looking at these yellow boxes, just consider them to be 1 kilowatt hour. That's 1 unit of energy. Okay, so now if you look at the vertical axis, you're going to see power value, which is in kilowatt. We said it's 8 kilowatt peak, so this is 8 kilowatts, and that's the peak right here. But of course, you know that solar PV cannot give you 8 kilowatt peak because of performance ratio. We discussed about performance ratio yesterday.
Hello, please. You are not audible enough. I'm struggling to hear you.
Is that the same for every other person?
Yes.
Okay, has it improved now?
I'm hearing you.
Yeah, it's better now. It's better now.
It has improved. Okay,
Yes.
okay. Thank you for pointing that out. Okay, so what I'm saying is that you should consider every of this.
Please send a chat message. Just change the time. I'm replying to everybody. Thank you. Continue.
Okay, I think the issue is that some of them here we are not present yesterday. So
yeah,
if you're not here yesterday, please Engineer Uche will share a video for yesterday. Just be patient.
I will share it.
Catch up. Yes, we'll still catch up with whatever you feel you've lost yesterday. It's recorded, so you can actually go back.
It's recorded.
Yes. So what I'm saying is that every of this yellow box you're seeing here, just consider it to be 1 unit of energy, which is 1 kilowatt hour. And I did say that the reason why you can this yellow box didn't get up to 8 kilowatt peak is because of the performance ratio. Okay, which in some cases can be 60%, 70 or 80%, depending on the weather condition of where your solar system has been installed. Those of you that were at the training yesterday can easily understand what this means. So this is the simplified daily demand profile with 10 kilowatts peak load. Remember, our solar system is 8 kilowatt, but the peak of your profile is 10 kilowatt peak. Now, it is assumed that you don't have any PV system in this instance now. So all your power demand, all your power consumption is coming from the grid. And that's why you have 100% coming from the grid in this portion of the diagram. Okay. So remember, I said that every one of these boxes represents a unit of energy. So if you count all of these boxes here, it's going to give you 163 kilowatt hour daily. If you calculate that for a year, you're going to get about 4,900 kilowatt hour. Sorry, if you calculate that for month by month, you're going to get about 4,900 kilowatt hour in a month. So just this represents energy consumption along the path of the energy profile. So when we embed this 8 kilowatt peak solar panel into that load profile, this is what it's going to look like. And this is actually a good design. Now it is assumed that this is a simplified daily demand profile with 10 kilowatt peak load and 8 kilowatt peak PV system installed. Okay. In this case, it is assumed that there is no battery storage. So every unit of energy that comes from the sun is being consumed, it's absorbed by the load profile. And of course, you should know that this load profile is actually your consumption in the home or in the industry or whatever load that's whatever load the facility you're installing for, whatever their consumption pattern is, it's represented by this load profile. So now we are looking at the simplified daily demand profile with 10 kilowatt peak, and then now you've increased the solar installation from 8 kilowatts to 11 kilowatt, meaning that you've now exceeded the peak of your profile. So if you notice the sun part now, the yellow boxes, you find out it has now exceeded the profile at noon. That's when the sun is out. So you've exceeded it. So the problem here is that if you do this kind of design and then you're having this excess power from the sun and you don't have a battery storage system, it actually goes to waste. So this is over design. The system can be said to be over design unless you have a battery system that can absorb this. But in this case, it is assumed that it is connected to the grid. Okay. So if you look at this pie chart in this right side of the screen, you will see that 90% of your demand is, now the yellow portion is your power supply from the solar system. 90% of that is consumed directly. Okay, why 10% of it is feeding into the grid? Now, this is assuming that you have a grid-tied inverter, okay, that you can send to the grid. So only 10% is sent to the grid. And if you look below, you're going to see the demand that is covered by different supply sources. So 67% is covered by your grid, whereas 33% is covered by your PV directly. This yellow portion, okay? Now, let us increase that solar installation further. So if you increase it to 17 kilowatt peak, okay, this time it's way beyond the peak of your load profile, right? So the same thing that happens in the previous case will also happen here. But here, more of the energy will go into the grid. So let me know this is the same scenario with the previous one. It's just that more of your energy will not go into the grid. But there is a slight difference in this case. Now, this case now you're not having storage. And let me say this, that battery storage is still quite expensive. We've not gotten a breakthrough in that technology, so it's still quite expensive. So in your design, you try as much as possible where it can be allowed to do away with battery or reduce the need for batteries significantly, so that your design can still be viable in terms of investment wise. So now we are looking at the simplified daily demand profile of 10 kilowatt peak, and then with 17 kilowatt peak PV system installed, plus storage. Okay, this can be very good for an off-grid system. It can also be very good for a grid-tied system. So how does it work? During the day when the sun is fully out and you're consuming not all the energy that is coming from the sun, then the part of the energy that's coming from the sun that you're not consuming can then be stored in the battery system, so that at night when the sun is no longer out there, it can now blend with the grid. Okay, the energy from the battery can actually blend with that's coming from the grid, and then help you to reduce your consumption from the grid, and then actually reduce your energy consumption as well. I mean, cost. Now, this is a situation where we have 17 kilowatt peak we produce less on a cloudy day. So of course, we know on a cloudy day, your solar system will not perform optimally. So in that case, it's now being reduced even far below your load profile. So in this case, whatever is being produced by your solar system is actually consumed by you during the day. Okay, so this is more like the same case we had from the first diagram I showed you, where your solar system is actually within the limit of your load profile. Okay, let me talk about generators. If you notice the previous slide, I've not actually integrated generator, but here let us see how we can integrate generators and see if it's possible to eliminate the use of generator backup in our systems. So here is a business as usual situation. Okay, in this case, we assume that maybe on daily basis, you have 2 hours of outage. Of course, I know for the Nigerian situation, it is not ideal. In most cases, you have up to 12 hours of outage or even more. But notwithstanding, this is just for an illustrative purpose. Okay, so we assume that there is 2 hours of outage over 24-hour period. So we have a generator of 20 kVA. We don't have any solar PV installed. We don't have any storage. So this is just business as usual. Okay, if there is an outage from the grid. Now, these gray areas represent the grid. Now, this area represents the use of generator. This other area, sorry, represent the use of generators. That's 1 hour, for each column of them. So this is 1 hour. This is another 1 hour. So this is by 1 p.m. and this is by 8 p.m. The grid fails and you're running your generator. So this is business as usual. Now, if you have a solar system installed and then and it's connected to the grid, okay, you have a grid tied inverter, and your grid tied inverter actually disconnects anytime there's a grid failure. So if there's a grid failure, your inverter will just disconnect, in which case you will now start running your generator. And the reason why it's disconnected is that because you don't want to feed power into the grid when the entire grid has collapsed. Okay, so in this situation now, your inverter is not a hybrid inverter. It's not a hybrid in the sense that it cannot combine your power from your solar system.
Hello.
Hello. You have a question?
Hello.
Hello. You have a question, Stephen?
Hearing anything from my end here, please. I'm not hearing anything. I'm no longer a part of this this lecture.
So sorry about that.
Stephen, there's a problem from your end. You are muted, number one. Then you are, it's like you have two systems, if I'm not mistaken. You know, I told you I have an issue, and that might be a problem. So why not log off and log in again? Log off from every system, log in again. I will accept you, and then log in with your audio on, please. Thank you. Just log off. I hope you.
Okay, so Engineer Steven, I hope you heard that from Engineer Ushe. So now this is the system whereby we have an inverter that is connected to the grid, but it's not a smart inverter. It's not a hybrid inverter. So anytime the grid fails, there's an outage, it shuts your solar system, it doesn't work. Okay, so it's not a smart inverter in this case. So if that is the case, the excess energy that is coming from your solar system is formally being pushed to the grid, but now because the grid has failed by 1 o'clock, so it shuts off your solar system. It's not taking any supply from your solar system, in which case you have to run your generator. So in this case, you're still running your generator at 1 o'clock and at 8 p.m., right? However, because you have solar system installed that produces from 7 a.m. up until about 6 p.m., it reduces your dependency on the grid. Okay, so if you look at the pie chart here, you find out that 37% of your supply is now coming from the solar system, whereas 52% is coming from the grid and 10% is coming from your generator, just for these 2 hours that you have grid outage. Okay, let us.
Hello, Engineer Chima.
Yes, Stephen.
I have Chima, yes.
Okay.
Yeah.
Go ahead.
I have a question. You said in this case, the yellow area, I think the light yellow area is the area whereby you are supplying to the grid, but the grid failed at 1 p.m. So I'm thinking of if the grid failed at 1 p.m. and you are supplying to the grid, which is part of the green area, why is not going to be that your power demand will now be taken from the solar?
Yes, you're very correct. You're very correct. And that's why I say, now if you look at this, this is 1A, and we assume that when the grid failed, I said that the inverter in this case is not smart. There are hybrid inverters, yes, and there are inverters that are not. So you have different categories of inverters in the market. Okay, so if you look at our solar PV, yeah, it is grid connected. It is 17 kilowatt peak. But look at the next set of it. You have a hybrid controller. Okay. Now, in this next case, now it is assumed that even if the grid fails, now look at what we have here, stay connected during generator operation. So even if the grid fails, okay, your inverter can combine the power supply from your generator and the solar. It can combine both of them and they supply you. Whereas in this case, okay, if the grid fails and the solar doesn't have enough capacity to supply your consumption, what happens? So the inverter will just knock it off. It will not even take anything from it, right? But whereby you have a hybrid controller means that it can collect power from the generator and also collect the one that is coming from your solar, even as much as the grid is not there. So your generator is now serving as the grid, right? And it is also taking the supply that is coming from the solar and is combining both of them to supply your load. I don't know if that is clear to you now. So this is this.
Yes,
this is the situation in this case now. So there are different situations and there are different inverters in the market. So that's why when you go to the market, you need to know exactly the level of control that you need. Okay, and then you look for an inverter that has the capability to do that. That's why it's important I also illustrate all of these parts in this trailer. Okay. So now.
Hello, Engineer Shima.
Okay.
Hello, Engineer Shima.
Yes, I can hear you.
Hello.
I can hear you.
Okay, this arrangement of the solar with the generator, how can you explain it in terms of cost? If you want to use solar solely, maybe there's a grid follower, you are depending on the solar. Does that mean your solar, the capacity of solar will be bigger than when you are using the combined, the hybrid with the solar and the generator?
If you want to meet all your somebody's music is distracting. If you want to meet all your load with solar, anytime the grid fails, what that means is you're going to oversize that system because you want to meet all your load, which is not ideal. It's not the best. It's not an optimized design, right? So that is the situation. So for you to reduce those excessive costs, right? It's advised that you do a hybrid system where you can have instead of having oversized solar systems and all of that, you can actually combine it with your generator and then you optimize the entire system. Now your generator is scalable. Understand? It's scalable in the sense that if it's not, it can move along the path of your load demand, right? And it's also if it's burning so much, if it's meeting a higher demand, then it's burning more fuel. If it's meeting a lesser demand, it's burning lesser fuel. But it's not the same case with your solar system. Your solar system has a fixed upfront cost. Okay, so if you look at the financial viability of these two systems, sometimes it's better that you combine it to make a hybrid system whereby you can pick whatever that is coming from your solar system and augment it with your generator. I will get to the part of generator. We will also discuss about the downside of this arrangement and all of that. So in this case now you have a storage, a battery storage into it. Okay. So during the afternoon when the sun is fully out and then you are taking all that you need from the solar system, the excessive energy that is produced will not go to the battery storage. Now at night, then you can just discharge the battery when there is grid outage, okay, for 1 hour. This is
that's a waste of time for putting solar.
engineer, please note everyone.
Not that. No, that is not.
Okay, thank you. So, I mean, that is it for that section. Let me now switch on to what we have today. I just quickly rounded up what we needed to discuss yesterday. And
sorry, Mr. Chairman, manager. I don't know the material for today. Has it been shared?
Engineer Chicken. Engineer Chicken, have you distributed?
I've shared the what now. I know those who didn't come yesterday are the ones asking most of these questions, and I'm sorry about that. Because today I tried to send a reminder to everybody who registered. Now, the material is in a folder. So what I just did was to share the whole folder to us. So the folder inside there comprises of the whole 3 days module. So I've never shared any material in bits. Yeah, everything is in the folder.
Okay.
Yes, yeah.
Okay, no problem. I understand you, sir.
And if peradventure you didn't get the material, maybe because I'm not confirmed your payment or so. So just be
No. I've gotten it. Okay. I thought maybe they are different. So it's fine, sir.
Go ahead, sir. Thank you.
Okay, actually today, what I want us to discuss today is about solar PV design.
Sorry, but I have a question in just concluded
session.
Yes.
Go ahead and ask the question.
The question is this. I was thinking that the reason why people go for solar is to do away with generator. Why are we now doing hybrids using generator with solar? What's the reason?
Thank you.
Okay, so thank you very much. Thank you very much for your question. Now, it's all about cost. Okay, yeah. Everything boils down to cost. That's what we call levelized cost of energy. We even do that. We'll come to that in this solar system. That's what we call levelized cost of energy. Now, madam, let me ask you: if you're running a business, and if I'm coming to sell energy solution to you, and I say that okay, I'm going to give you solar, only pure solar, so you don't run your generator, but you're going to pay me 150 naira for a unit, okay? And I come to you and say, okay, madam, I'm going to do a hybrid solution for you. I'm going to mix solar and generator for you, and you're going to pay me 120 naira per unit of energy. Which option would you go with?
I'll go for the one that is less, which is solar.
No, I say solar, pure solar is 150 naira per unit.
Okay, 150 naira per
unit. And I want to combine it with generator to reduce the cost. And I say, okay, pure solar, solar and generator combined, you're going to pay me 120 naira per unit.
100.
Or 100. Or say 100. So which one would you?
I will go for one that is less costly. But if you come to establishing it, it may be costlier establishing it, because in only PV, you will not buy generator, because in the other one, you have to also think of the cost of the generator.
So there's what we call cost benefit analysis, and there's what we call levelized cost of.
Two of them may be different, because you will still be buying fuel for the generator. Or is it fuel less?
You're very correct.
Chima, can I just say this? Madam, you know, solar only operates when there's radiation. Unless you want to buy excessive battery. Madam, hold on. Unless you want to buy excessive battery. So what Chima is trying to tell you is that the idea of a hybrid system is a cost-dependent thing. It has to do with cost, because your solar can operate your services during the day. During the night, you cannot use solar, but you use stored energy in the battery. And now your load is a function of the capacity of your battery. So if you end up buying a battery that's worth 2 million naira, and there's a generator you can buy for 500,000, that will serve the same purpose. Just like what he said, the major criteria is what is the cost of per kilowatt. It doesn't make sense whether it's coming from solar or from any other source. At the end of the day, the consumer is interested in cheaper costs. Well, Chima will say more on this, but I just want to say it in the layman's language. Thank you.
We are exactly saying the same thing. Sorry, I want to really understand it, because if you think about buying extra battery to have extra storage to serve you in the night, what of the cost of getting generator and getting fuel as well? It is also
there will be. Yeah, you will do the cost benefit analysis. You will do the cost. We will do at it and look at the payback, look at the internal rate of return. That's the one we do. In the other cost we do, the one we call energy auditing and energy efficiency. Unfortunately, this one is about design, but that one now talks about the cost. Even though on the third day of this class, we'll try to do a little bit about that cost. But when you do the two costs over a period of years, you will see which one is cheaper.
Okay, so just
I think what she's saying, it depends on the importance of equipment you are using it for. If the equipment is such that it cannot do 1 minute without light, it is better you forget about cost and make sure that the equipment remain working. So that's what the man is discussing.
And looking at the output and be looking at the generated income, which you can use to offset the cost of instituting the structure.
You need to do mathematics. You need to do the figures.
So madam,
we can't do it here now.
Yeah, we'll get to that part where we are going to do the levelized cost of energy for solar systems. Yeah. Now, for every energy system, whether solar, generator, geothermal, whatever energy system that you are considering, the bottom line is what is your levelized cost of energy? Now, levelized cost of energy is the energy that system is going to generate for its entire life, right?
Okay.
You bring everything to bear, you check the cost, so you determine how much every unit of energy is going to cost. When you compare them across technology, you just take your decision.
Okay.
Go ahead.
Okay, another of my question is, when this solar is generated, how is it connected to the grid?
Were you at yesterday's class?
No, I wasn't there.
So
I know it was to use the inverter, but that inverter, is it going to EEDC straight? That's my question.
We have discussed all this yesterday. I will encourage you to look at yesterday's video.
Madam, I'll send you the video now. I'll send you the video now.
To my WhatsApp.
Chat me on WhatsApp, man. Let's continue. Chat me on WhatsApp.
Do you have my WhatsApp number?
You are having mine. Okay, I will chat you now.
Hello, good afternoon.
Good afternoon.
Hello,
sir.
good afternoon. Yeah, good
Yes,
afternoon.
sir.
Engineer Shuma, well done, sir.
Yes.
Yes, please. I am actually enjoying this course and I have been following since yesterday. and I just decided to keep mute since that yesterday because my network was somehow, I was actually battling with it. But I just concluded our section you just finished before you start the new topic for today. You said something about oversizing the panels for in our design.
Yep.
That is not actually cost economical, if I'm not mistaken. Am I right?
Okay. Yes.
Yes. I just want to shift this in, or maybe an observation, or I stand to be corrected anyways.
Go ahead.
I think this will depend on the designs we are looking at. Let me say this. Firstly, if you are looking at, okay, what is our daytime load and what's our night load? We can actually, I personally think we can actually oversize our system or size our system to meet our daytime load, while the battery backup will serve for the night load. Am I right? So
you're correct.
Some design, you can have a kind of panel array or arrangement that will be sized up to your daytime load, while you have your minimal backup time in the night load, so that your cost for battery is so high, while intending to match up the daytime and nighttime. That's why I think that sizing up your battery for daytime load will actually sometimes require you to oversize your panel to meet up such load based on your design, so that you have minimum of battery to nighttime, and of course the cost will be reduced. Just an observation.
Yes, you're correct. Now, when I say oversized, now this is my definition of oversized. Okay, oversizing in my own definition means that you don't design a system whereby you have redundancy. So you have oversized panel whereby your batteries are filled up. You've used all the energy coming from, and yet you see excess energy that is not going anywhere. That is oversizing in my own definition.
Okay. That is must be well sized with your load.
Yes, you must be well sized with the load.
All right.
Exactly.
Thank
Whether
you.
nighttime load or daytime load, size it up.
All right. Thank you.
So that at any point in time you don't have a redundant.
All right. All right. Wow. Well captured.
Okay. Thank you. So let's go ahead with this.
Sorry, Engineer Chima.
Okay.
Although I don't know if it is in another course or it will be touched on later, but with the solar system or PV system, do you put into consideration, say, if it is an industrial area you are designing for?
Can you say that again? Sorry, please. There was a sound that distracted. Distracted me from hearing you. Go ahead. Just repeat your question.
Okay. What I'm saying is, when you are designing for, say, an industrial system,
okay,
or an industrial load arrangement,
okay,
do you put into consideration, or how would you account for the requirement of kilowatt for large inductive motors and those kind of loads that require the supply of bar, not only the supply of kilowatt?
Yeah. Okay. We in our previous training, we will talk about energy audit and energy efficiency. We dealt in details regarding those areas that you're talking about. However, that's why I say it is very important for you to do any solar PV design, any solar system. You should first of all get your load profile, obtain your load profile. So if you see your load profile and you see there's an overshoot somewhere and it's being caused by an inductive motor and all of that, then you can now begin to apply your energy management skills. So, for example, is it possible to meet those high peak? Because they could be they're transient. They're not always there. I mean, they just come, maybe you're starting up your heavy industrial motor and you see that shoot in your load profile. You cannot size your solar system to meet that high peak, because after that period, for every other time, you have a high level of redundancy, right? So could it be possible for you to bring in a generator to meet that very high spike? And when it's come down, it transfers the load back to your solar system. So there are ways to work around all of this. But most importantly is to have your load profile. Your load profile is the basics of your design. You understand how this facility consumes energy, how their demand at every point in time, you know. If you're not speaking, please mute yourself so that you don't distract the class. Okay, so like I said, the most important thing in your design is to obtain a load profile of the facility. With that, you can work around everything. That is where your engineering skills comes in.
Can I ask a question?
Go ahead.
Go ahead, please.
Please, can I ask a question?
Go ahead, sir.
Yeah, like the last speaker was talking about. I was trying to respond to what the answer you gave.
Mm-hmm.
Hello?
I can hear you, sir.
I was trying to respond to the answer you gave.
Mm-hmm.
That when you have a spike occasioned by industrial motor, you will call a generator to duty. At such a, do you quickly calling the generator to duty that was not originally online? I'm just wondering what kind of system do you put in place to quickly call a generator to duty?
No, for industrial motor to come
to respond to such a spike.
For industrial motor to come on, someone has to switch it on. It doesn't just come on automatically for an industrial motor. Someone has to switch it on, right? I mean, this is just me thinking on top of my head now. Someone has to switch it on. So before the person switches it on, then you can make adequate arrangement to take that spike. If that's the case. Hello, can you hear me?
No, sometimes.
Go ahead.
No, I think. Sorry, can I say something?
No, hold on. Let us hold on, please. Everyone, hold on. Let us not.
Yeah, I was saying that.
Hold on, sir. We'll get to that. And I remember there is a section. In fact, in today's training, we'll get to that. Please hold on, so that we can run through this training. If after this training, if that question is not addressed, we can then discuss it so that we don't spend so much time around this. I know there's a section in this training that, in fact, I have a load profile for an industrial process where we combine with generator and everything to talk about how you meet up all of this. If there is a spike, don't worry, we're going to go through it so that we don't
repeat ourselves.
Yeah, so let me just proceed, please.
Thank you, sir.
All right, thank you.
Okay. So solar PV design and sizing, we're going to do a little bit of calculation in this case now. So first of all, when you're doing a design, the most important thing is the load that you want to power. So get information as much as possible about the load that you want to power, because those are the things that will inform. There's a background noise somewhere. Please mute yourself if you're not speaking so we can move on smoothly with this class. So the most important thing are the load that you want to power. So you need to first of all take an inventory. You have to do a load audit of the load that you want to power to determine the energy that is required and the power that is required to meet those loads. Mind you, that energy and power are two different things. So these two things are very, very important. The power that is required and the energy that is required. If you have these two things, then you are good to go. And then again, you have to also establish your load profile. Okay, so three things very, very critical. Your load profile, the energy that is required, and the power that is required. Okay. So this is a sample electrical load detail. Okay. Now this is just for simplicity's sake, right? So we just assume television, the quantity is 4, fridge 1, lighting bulb 8, standing fan 1, and these are their power ratings. So in all, we require 255 watts, okay, which is about 0.255 kilowatts of power. So we know what our power is. Then secondly, we need to determine the number of hours that they use this load. So for television, we assume that they're going to run it for 6 hours on daily basis. Okay, for the fridge, 12 hours, for the lighting bulbs, 8 hours, and for the standing fan, So this is why it's very, very important you conduct a load assessment or an energy audit before you install a solar system. It's not a good thing for you to guess that, okay, or in as much as this load audit is an estimate, it's not accurate, but it gives you a pointer, okay, of how to size so you don't oversize and you don't undersize. Okay, even though you've done all of this loading, you still give your tolerance and all of that. You still give your margins and all of that. So now we know what the power demand requirement would be. Based on the hours of usage, we can now establish the energy that is required. So here we have established that it requires 4,000 watts hour per day. 4,000 watt hour per day. So let us now size solar system for this kind of a system. Okay. So of course we know that our peak demand is 255. Mind you that this peak demand that we have here, this is a peak demand. It should not always be the case because sometimes this fan might not be running. Sometimes the bulbs might not be on. Sometimes, so they may all not on. They may not all be on at the same time. Okay. So we assume that this is a peak load. I mean, assume that everything is on at the same time. So this is our peak load. It's an assumption. So if our peak load is 255 watts, okay. So now inverters. Now we all know that inverters are rated in apparent power. There are different kinds of power. There's real power. There's apparent power, and there's reactive power. Okay. So inverters are rated in apparent power, the same way your generators are rated in apparent power. That is kVA. Okay. Yeah, but I'm using VA. That's volt amperage in this case. So therefore, assuming a power factor of 80, of course, we know that if you need to convert from apparent power to real power, you have to apply a power factor. Okay. So let us assume that our power factor, because this peak that we want to meet is in real power, is in watts, and our inverters is rated in apparent power, which is VA. Okay. So we want to determine what will be the size of the inverter in VA, okay, to meet this load, right? So we have to apply power factor to convert this real power to apparent power, and that's why we have to assume a power factor of 80%. You can assume 90%, you can assume 75%, you can even assume 100%, assume that it's a resistive load. Okay, so just assume your power factor, but this is just an assumption. And a desired load factor of 70%. Now, if you're running your generator, it is not every time your generator, in fact, you don't run your generator at 100%. Okay. At every point in time, your generator is running at a certain load factor, which in some cases could be 30, it could be 40, it could be 80, right? So in this case, let us assume that the maximum amount of load that you want to put on that inverter is 70%. Okay, that's your desired load factor. So you have a tolerance of 30%. Okay, so all of those things has to come to bear if you want to determine the size of inverter that will carry this load, and then give you this tolerance of 70% load factor and a power factor of 80%. Okay, so now this is how we calculate our inverter size. Our inverter size will now be equal to the peak demand, which is this 255, divided by the power factor times the load factor. Okay, so if you plug in our values here, you have your peak demand, which is 255. You have your power factor, which is 0.8, which is something like 80%, times your 0.7. So when you do this calculation, you're going to have 455.33 VA. So if you want to power this load, you can comfortably buy an inverter of this capacity. Of course, you can mark it up to 500. Okay. Then you can.
Chima.
Yes.
I'm a bit confused about the 0.7.
0.7.
Yeah.
Okay. So if you have a generator, right? I'm assuming that you have a generator. So if you have a generator, so for example, you have a 5 kVA generator.
Are you talking about generator now or solar panel?
Okay.
Trying to get better for a solar panel.
Okay, sorry if I'm confusion here. Now your inverter is serving almost the same purpose, not the same, but almost the same purpose with your generator.
It's synonymous.
Yeah, it's synonymous with it. So I'm just trying to make an example with generator that you can easily relate with.
Relate with, yeah.
Okay. So when I use generator, I'm not trying to bring in generator in this time, just to make you understand the concept that we are applying in the case of inverter. Okay. But if you still don't get it, please ask. No. Yes.
Can you just spend 1 minute?
Okay, go ahead.
Okay. The engineer, I don't know the name of the engineer. The 70% is also like what we discussed yesterday. It's also like another safety factor. In other words, you don't load your generator 100%. Your inverter will not be operating at 100%. So this 70% is like you are saying, at every point in time, I can load it to 70% maximum. And I also told people yesterday, somebody coming from the water angle, when you design pipe that will convey water, the code and standard says that the water in your pipe must flow between 70 and 90%. That's what the standard says. Why they say between 90 and 70% is that if you exceed 90%, you're overloading that pipe. And if there's any water hammer, if there's any pressure push in that pipe, the pipe will burst. So if you have a house, for instance, it is not necessary that all the rooms will be occupied by the total exact number of persons required. So that is just see it from that angle, from a layman's language. So 70% is saying at every point in time, I'm loading 70% of my load. And that is what the load factor is.
So that's, thank you very much, Engineer for that. And again, just to add to that, you want to maintain the value of 70%. So for example, what if somebody mistakenly add additional load, or maybe you've actually bought this inverter, and at the time you bought this inverter, you didn't know you were going to buy, so for example, you didn't know you're going to buy, you're going to add additional bulbs to your home, or you're going to buy additional TV to your home, right? So if you design for 70% and then you eventually buy additional television in your home, okay, it can increase that 70% to 75 or 80%. So that's the tolerance we're talking about here. Okay, so it's a safety margin as well.
That is when the power factor is 30%.
Sorry?
I said
hello
about factor being up to 75% when the power factor is of 80%.
These are two different things.
Chima, let me come again. Power factor is a completely different thing. Power factor, as Chima said, we have what we call real power, reactive power, and apparent power. If you draw the power diagram, the one we draw like a rectangle, yes. Some loads are reactive. So that one is a different thing. It's completely, this one is load, this one is power factor. The power factor is, the apparent factor is the hypotenuse of the, this is mathematics now, sorry.
Of the, sorry, in generation, because.
Hello, please. Hello.
Hello. See, please. Now, the way we have structured this training is that we first, like all these questions that I did ask now, if everyone were present in our last training, this question will even become, because we structure it so that we first of all walk you through all of these power tech terminologies, energy auditing, and energy efficiency before this training. We have done that training. Was it 2 months ago?
Can I share? Okay, let me share that material with them, please. Anybody has question on some of these technicalities, I'm going to share a free material, Chima, with your consent, okay? With all our consent. Okay. Let me share that material with us, but that material is part of our energy auditing and energy efficiency class, but it's like a foundation class so that all this load factor, power factor will be a thing of the past. So I'm going to share with us now, okay? So all of you in training. In the chat box. No, in the chat box now. I'll just go to chat box and download it. I'll share it. I promise you. Chima, please continue. I know why Chima is saying this. We might lose time. We have a lot to cover.
So I requested from WhatsApp the recording of yesterday. No response yet.
I shared it before we ended yesterday. I shared the video of the day one.
Where did you share it, sir?
Before we ended yesterday, sir, I shared it.
Where did you share it? I didn't pick it up. Please, can you reshare?
I'll do that, sir. I'll do that now.
I chatted you up. I sent you the message on the WhatsApp.
I sent hi to you in my WhatsApp, but you are not on.
Madam, I'm on. I'll share it.
I also sent to you too, sir. Okay.
Okay, I'll share it now. Let's continue. Let's allow Engineer Chima continue. Thank you.
Okay, so yeah. So,
excuse me. Can I speak?
Go ahead, please.
Go ahead, sir.
I think we need to bring in some structure into the class. Much as Engineer Chima wants it to be interactive, I think we need to have some time to be asking questions, because if we keep discussing, like it's been said, we'll just lose the time. Yesterday after 6, we have not covered, and Engineer Chima has to
rush through some of the material. I think if we
hello, Chima.
Yes, okay. Please let us abide by the rule. If you have questions, please note it down.
Hello, Chima.
Hello, I can hear you. I can hear you, sir.
Hello, Engineer Chima.
I can hear you, sir.
Hello.
I can hear you, sir. I can hear you.
His network is what?
His network is not good.
I think
he's the one not hearing me. Please, let's proceed.
From his network. Let's proceed, please. Yeah, so I can cover what
a bit different scenario, different thing altogether. Okay, Mr. Okay, Chima. Hello.
Okay. Yes.
I'm hearing you well.
Okay.
I'm hearing you well. Are you hearing me?
I'm hearing you too.
So what I'm saying, okay, now in the last course, I paid and I didn't attend. So when I sent out
sir, please, can you sort that out with, can you sort it out with engineer?
They told me, chat me up, sir. I'm sorry.
I was going to be listed on the next course.
Okay.
Hello.
You will, sir. I promise.
You mean
I
should sort it out with who?
I'll chat me up, sir. Now chat me up, sir. I will respond.
Please, please handle that so that we can continue with the class. Sorry about that. Sorry, I'm so sorry about that.
Sorry about that, sir. Apology.
Yes.
Just chat me on WhatsApp, sir. Don't worry. Let's continue.
Try please. That in WhatsApp.
Let's just continue, please. I'm sorry about that. So, but let's continue. So we can finish up this at our scheduled time, please.
Okay, continue. I've seen the WhatsApp. I will respond now.
Okay. So there's a little exercise here, just for us to, because I want us to be, I want this to be practical. It's not a difficult thing. Just pick this formula, pick the values in this question, and then you plug it, and then tell me your answer. Please, let's just try this. I believe if you don't have a calculator, your phone should be closed. Just use your phone to do this, and see if you get the answer correctly. This is just an exercise. Calculate the inverter size required if the peak demand is 400 watts. In our first example, it was 255. Now the power factor in this case is 85, and the desired load factor is 60. Now, and this is to allow for future load addition. So can you just quickly punch your calculator and tell me what will be the required inverter size?
784 VA.
700 and
put in the chat. Put in the chat box.
Do you want us to do it?
Put in the chat box.
Yes.
Please on the chat box. Put in the chat box.
Do you want us to answer the question?
Yes, ma'am. Put it on the chat box. The answer. Thank you. Exercise 1. Put the answer on the chat box. We need 5 people to respond. Then we'll continue. Thank you. Two people have replied.
If you're having any challenge trying to solve this, let us know.
I don't know if you are seeing my message.
Yeah, I've seen 3 people now.
Ejime Stanley has replied.
Engineer Lawal, check your answer again. Check your answer again. The peak load, after calculating the peak demand in watts, is 400. And the power factor is 85.
Okay.
784.
Good. Thank you.
Sorry.
Sorry, and I gave an approximate value, although it's 784.31.
Yeah, you now size the biggest battery. So that will be 4 batteries, 200 ampere Oh, Chima, sorry to preempt you.
Yeah,
okay.
No worries. We'll get to that. Okay. Okay, so let me proceed. I just want us to keep trying this so that should in case if maybe there's any confusion, it can be clarified. Now let's move ahead. So now sizing of battery. Okay. Now let us take the same load that we had. You know, in our load calculation, we had 4,000 watts hour, right? So let us size for this battery system. Okay. So when you want to size for your battery, the reason you're using a battery is to be able to one, to provide power when there is no sun out there, and two, maybe when there is no enough supply from the sun, you can pick from the battery and then supply. But these are the essence, these are the reasons you need battery support. Okay, so in sizing your battery, you have to also take into the consideration that there could be some days when the sun will not be out. Okay, and we call that days of autonomy. Days of autonomy simply means the days when the sun will not be out, a cloudy day that the sun will not be out for that day. Of course, it do happen, okay? So you have to also take that into consideration. And in some cases, you can say, okay, I'm considering only 2 days of autonomy. So for 2 days, there is no sun, and I want my solar system to keep working. I want my battery to keep supporting my load for that 2 days, or for 3 days, or you can do it even 1 day, right? So that is the essence of having a battery storage system. So you have to take this into consideration. So in our exercise, I'm considering 3 days of backup when there is no sun. So 3 days of autonomy. So if you do that, you're going to multiply your daily energy need by that 3 days. When you do that, you're going to have 12,000 watt hour. So I'm sizing my battery to be able to deliver 12,000 watt hour. Okay. Okay. So how do we do that? So, however, 12,000 watt hour is the usable size for a battery with 50% depth of discharge. This is typical for lead acid batteries. The battery size will be given by, now let us size this battery. I hope we all understand what DOD means, depth of discharge. It means that if the battery can hold 100 units of energy, it can only give out 50 units of that energy to remain in good shape. If you take more than 50%, that battery can damage quickly before its life cycle ends, right? So that's what we mean by depth of discharge. So it can only give us 50 and retain 50 for that battery to remain to keep performing at optimum level all the lifetime. Okay, so that's what depth of discharge means. And this is very, very typical for lead acid battery. I mean, 50% is typical for lead acid battery. If you're using lead ion, lithium ion, if you're using lithium ion battery, it can go as high as 90%. It can give out as high as 90%. Okay, so those are the difference in terms of battery categories. So now let us do the battery sizing. So if you want to do a battery sizing, you're going to consider the usable capacity. In our own case, the usable capacity is 12,000 watt hour. Okay. Yes. So so if you now consider the days, sorry, okay, I think this wasn't complete. So this is the complete equation. Okay, so you have to consider the usable capacity, and you're going to divide it by the DOD, depth of discharge. Okay, so our usable capacity is 12,000 watt hour, and our DOD, which is depth of discharge, is 50% or 0.5. Okay, so if you do that division, you're going to have 24,000 watt hour. So this is the battery size that you require to be able to deliver 12,000 watt hour of energy, assuming that taking into consideration that the sun may not be out for 3 days in some certain cases, in some certain situations. Okay, so this is how you be able to calculate the size of the battery of your system. So now the next is to calculating the energy content of your battery. Okay, I'm going to show because this is the energy that your battery is going to give out. But you need to also know how to calculate the energy content of your battery. Okay, so that's what I want to explain now. Because of course, you know that when you buy a battery, you're not going to see you're not going to see anything in watt hour. You can't see that in a battery. So how do you relate this watt hour with the things you see on your battery. That's the essence of this. So batteries are rated in voltage and amp hour. This is what you're going to see on your battery. So how do you convert this voltage and amp hour into watt hour? Okay, for many of us that has electrical engineering background, and you should know this. This is just a simple electrical calculation. So we know that our power is equal to voltage times current. That is it. Okay. Now you notice that I put times PF in very faint color. Okay, because ideally voltage times current is apparent power, not real power. But we are talking about real power in this case. So, but let us just ignore that. Okay, if you notice my unit is in real power, but for you to have real power, you must convert it with power factor. But let us neglect. That's why I put it in faint color, in faint ink. Okay, well, just neglect that. Okay, so we have voltage times current. Okay, now okay, so energy. Now this E here is represent energy. That's, I'm just trying to get hold of why I have E here. So this E here represents energy, right? Now this is power. Power is equal to voltage times current. Now energy is equal to voltage times current times time. Okay. Now these two, current times time is equal to amp hour. Current times time is equal to amp hour. So let us replace this IT, current times time. Let us represent it with AH. So your energy will now be equal to voltage times AH, which will now equal to this watt hour, which now corresponds to this watt hour that we have here. I hope no one is lost in this simple calculation that I'm showing. Okay, I gave a definition of every value that I have this here, where P is equal to power, E is equal to energy, V is equal to voltage, I is equal to current, and the AH is amp hour, which is what you see on your battery. You see amp hour and you see voltage. In most cases, you're going to see 200 amp hour and 12 volt. So when you see those, you can be able to convert those variables into watt hour. So let's just do an example. Okay, battery size example. So calculate the number of batteries required to produce 4 kilowatt hour of daily energy need, plus 3 days of autonomy. Okay, for cloudy and non-sunny days using lead acid batteries with the following ratings. Now you have a 12 volts battery, you have 200 amp hour battery. Okay, your battery is 12 volts and it's 200 amp hour. And of course, being that is an lead acid battery, you have 12, you have 50% DOD. So let's just do that calculation here. So now daily energy needs, according to our question, is 4 kilowatt hour. This is 4 kilowatt hour. Now daily energy needs plus 3 days of autonomy is 4 times 3, which is equal to 12 kilowatt hour. Please let us bear in mind that I'm using kilowatt hour here. In my previous illustration, it was watt hour. And I hope we understand that how to convert from watt hour to kilowatt hour. It's just a function of dividing by 1000. Okay. So now the actual battery size at 50% DOD. Okay. We apply that formula that I showed us in the other slide. The usable energy that you require divided by the DOD, that is 50%. And when you do that, you're going to have 24 kilowatt hour. Okay, so now this is the energy that you require from that battery. Okay, so how do we now, let us now calculate the energy content of every battery. So one of the battery, let us determine the energy content of one battery. Now, specific storage capacity of a battery is 12 volts times 200 amp hour, which will give us 2,400 watt hour. Now we have to convert it to kilowatt hour. So when we divide it by 1000, we have 2.4 kilowatt hour. So one battery will give us 2.4 kilowatt hour, but we want 24 kilowatt hour. So what we are going to do now is to divide 24 kilowatt hour by this energy storage of one battery. Okay. Sorry, this is kilowatt hour, not watt hour. There's K here. There should be K here. So when you do this division, okay, you're going to have 10 battery. So this is to tell you that you need 10 battery of this specification to be able to deliver 12, okay, to be able to deliver 4 kilowatt hour plus 3 days of autonomy in case of there is no cloud, there is no sun for the day. I hope this is clear. So if that's clear, let us do a simple exercise again. This is exercise 2. So calculate the number of batteries required, assuming 1 day of autonomy is required using lithium-ion battery with a TOD of 80%, 12 volt and 100 amp hour. Let us just do this on our own and then post our results.
We'll have 5 minutes. This time we'll have 5 minutes.
5 minutes. Yes, yes.
Okay, sir. Okay, sir.
I've resumed it.
Okay, okay. So let's go ahead now.
So we've done battery sizing, we've done inverter sizing. Now we're moving to PV array. Go ahead, sir.
Okay, so now let us size our PV system. Okay, so using the same sample load details in the data from the previous example. Remember that our load, the load we need to power is 24,000 watt hour. Remember, that's what we calculated considering 3 days of autonomy from our. No, not considering 3 days of autonomy. No, it is 12,000 watt hour. Then if you're considering 50% depth of discharge, we'll now divide it and then we got 24,000 watt hour, right? Because that solar panel needs to charge that battery to 24,000 watt hour. So we are sizing a panel that can charge our battery at this and then still supply for regular use and all of that, okay? So required solar PV energy output is 24,000 watt hour, okay? So let us now size that panel. Now, we have to consider what we call the peak sun hours. Those of you that were there yesterday, you should understand what this peak sun hour is now. So now, for example, we are taking 6 hours, example for Nigeria, okay? Yeah, when you're doing your design, please don't use 6 hours for Nigeria. Use 4 or 5. If you're in the southern part of Nigeria, just for safety margin, you can use 4. If you're in the northern part of Nigeria, use 5. But don't use 6, please. This is just for illustration, okay? Yeah. So our PV size, now here is the formula to calculate your PV size, okay? Required energy output divided by the peak sun hour, okay? That is just a simple calculation. Your required energy output, you divide it by your peak sun hour. So our required energy output is 24,000 watt hour. You are not dividing it by the 6 hours. So the hour, we cancel the hour. And you're now left with watts. And your solar panels are rated in watts. Okay? So when you do that division, you will have 4,000 watts. Now, mind you, you have to be careful. Mind you that the 4,000 watt is at theoretical, at standard test condition, which is theoretical. Okay? Assuming that that solar panel is performing at 25 degrees centigrade, 1,000 watts per meter square. These are the conditions at standard test conditions. So you also have to consider some safety margins, okay, which is where your performance ratio comes into play now, okay? So the actual PV size that you're going to require is the theoretical calculation that you got at standard test condition divided by your performance ratio, okay? So we'll assume a performance ratio of 80%. Okay, if you assume a performance ratio of 80%, then your actual PV size will be 4,000 watts divided by 80%, which is 0.8. Then your required PV size will now become 5,000 watts. So you need 5,000 watts PV system. I hope this is clear. It's a simple, these are simple calculation, but you need to understand these formulas and every terminology, what every terminology means. That was why I took my time yesterday to explain all of these terminologies before coming into these calculations. We've dealt with standard test condition, we've dealt with push peak sun hours, we've dealt with performance ratio, so you understand what all this means in these calculations. So I think there is another exercise for us to do here, just a simple exercise. Calculate the actual PV size if the peak sun hour is 5 and the performance ratio is 65. Please let us quickly do this and post our answers.
I'll pause the recording again. So we'll have another 5 minutes, please.
Okay, so let's proceed. Now, so there's another angle to it. There's another calculation that we need to do. Sizing of solar charge controller. Okay, remember that you have batteries, you need charge controllers to charge those batteries and all of that. And most times, you can either buy the charge controller separately, or some inverters have charge controllers embedded in them and all of that. So using the same sample load details and data from the previous example, okay? Now, these are the data, battery capacity. So we want to charge a battery that has a capacity of 24,000 watt hour. Now, the voltage of that battery is 12 volts in our previous example. So the solar PV array, we assume it to be 5,000 watts. Remember, you calculated 4,000, okay, yeah, 5,000 watts, right? In our previous example, not the exercise, in our previous example, we got 5,000 watts.
Ginachima.
Yep.
Why not just tell them number? Maybe if they're using 200 watt panel, maybe, or is it further in the class?
Yes. Yeah.
Okay.
So, no. I mean,
number since it's 5.
No, if you're using 300 watts panel, you cannot divide 5,000 by 300 to tell you the number of panel that you need. I think this is just a simple calculation anyone can do. Right. Okay. But it's good you raise that issue. You know,
just emphasize on it, because that's the end from a layman's perspective. Just
yeah.
Hit on it.
So if now when the thing is this,
you can do it in Word. You can project a Word document. Or your calculator.
I can just say this. If anybody is not clear about it, then you can say I can explain for that. But the point is that this is the total amount of solar panel that you need. Okay, so if you now go to the market and you now see a 200 watt panel, you only divide this 5,000 by 200, and it tells you the number of solar panel that you need to buy to make up this 5,000 watts.
Yeah,
that's what engineer.
25 units. Yeah,
that's what engineer is saying in essence. Okay. But if anybody needs further explanation, please, you can put that in the chat and I will respond.
Why I say that is that last week I was impressed. The one company said they developed a 670 watts panel, and before now I know that a 250 watt panel is about 2.1 by 2.4 meters. No, 2.1 by 1.2 meters. And another company now saying they've developed something times 2 of it. So that gives us hope that things are getting, I saw it. China already has 400. But what a company came up with. So before the end of next year, you're going to have a 1,000 watt panel of 1.2 meter by 2.1 meter. I'm pretty sure of that. Thank you.
Okay. Good. Interesting. So let us do a calculation for charge controller. And we know what the charge controller does. Charge controller charges the battery. Okay. It's just passes the right amount of current that can charge the battery appropriately. So using the same sample load details in our previous example of a battery capacity of 24,000 watt hour, battery voltage is 12 volts, solar PV array is 5,000 watts. So what charge controller do we need to charge this battery? Okay. So required charge controller is just given by this formula, the solar PV size divided by the battery voltage. Solar PV size divided by the battery voltage. Now, the size of your charge controller is rated in amps. Okay. Now, if you look at what we have here, if you use these values that we have here, your solar PV size is 5,000. If you divide it by 12 volts, okay, remember that your watts, this watts is equals to voltage times current. So if you open it up, the voltage here will cancel out this voltage here, and you have only amp that is left out, right? So this is how it plays out. So that your answer comes out in amp, that's amperage, which is the unit of current. So required solar charge controller is 416.67 amp, assuming all other losses are neglected. Okay. So this is just a simple calculation to determine your charge controller size, because you need to determine your charge controller when you're doing your design. So note that increasing the battery voltage will reduce the capacity of the charge controller required to charge the batteries. Okay. So if you have if you have a low voltage battery system, what that will do for it is going to reduce the capacity of your charge controller. Okay, whereas the reverse is also the case. If you reduce the voltage of the battery, okay, to increase the size of your charge controller. Okay, so if you want to save money, on charge controller, okay, what you're just going to do is to increase the battery voltage, and then you reduce the size of your charge controller. So in summary, we have finished our design now. Okay, so we need a charge controller of 416.67 amp. Okay, that's charge controller that is required to support 5,000 watts solar PV array to charge 4,000 watt-hour battery storage. This is all you need in a solar PV system: the panel, the battery sizing, the charge controller, and then what else? I think that's all you require. So we've now, we've gone through these calculations, and if there's any area that is not clear or that is confusing, you can speak up. Otherwise, let's just go ahead.
Okay, I will ask that. Okay, sir.
All right. So is this just for example's sake, or is it practicable?
Sorry, is this what?
Just for this example, is this for just for example's sake? Is it practicable for us to have a charge controller? Is it practicable?
Yes, of course.
For us to have a charge controller of 416.67 amps.
Okay.
A system of 5,000 watts panel.
Please, if you're not speaking,
I could hear some background noise. Yeah.
Okay. So now, what regard to the question that you're asking about the charge controller and all of that. Now, this is you can actually wrap this up to a whole number, right? You're not going to see a charge controller of 416.67 in the market, okay? But it gives you a range of what charge controller you need for that system. Okay.
My own question will be.
Please, I see. Just sorry, bro. Just 1 minute. Let's look for practical point of view. Anyways, let's assume we are using 360 watts capacity of panel. I mean, the panel we are choosing is 360 watts.
Mm-hmm.
So if we divide 360 by 5,000 watts, you're going to get 13.8. That is 14 panels.
Hold on. 360. The size of your
let's
panel.
Assume.
Okay.
The size of the panel we are choosing is 360 watts. So 360 watts divided by 5,000 watts, that will be 14 panels, right?
That's 5,000 divided by 360.
Yeah. Yes, that is 14 panels approximately.
Yes.
Now, for 14 panels, and we are introducing a charge controller of 416, that is like 420 amps controller. I think it is oversized practically. I think it's oversized practically just for 14 panels. Because I don't know, because these 360 panels I'm talking about just have the open circuit, I mean the IPP, that is maximum power, current power is 8.5 amps you can get from it. So if you connect it either in series or in parallel, you can add up to 416.
Yes, I understand what you're saying.
So you can't get up, and I know that's one of the critical things we must actually look out in our design. I stand to be corrected.
You're very exactly. You're very correct. Yes. So these are the things you look at in your design, right? Now, remember I talked about there are parameters you can put to if it's very, very impracticable for you to have this, you can now begin to tinker your design, your voltage. You can begin to consider the voltage that you're having for your systems and all of that, which will automatically change the charge controller size that you need.
Engineer, did you get it, sir? For me, I think the system, to answer his question, this system will not work with 12-volt battery. That's just it. And these days, I think the people will go for something of more of a 48 volts. So meaning that you put the batteries in parallel to achieve that voltage.
He's not speaking. Does anyone, any other person, has somebody wanted to say something?
Yeah, Kemi, Christoph want to say something.
Okay, I wanted to ask, equally important is your time of the time it takes for your battery to charge. So if we are assuming this a calculation of 420 amps controller for this service, looking at the fact that we were looking at a 24,000 amp hour capacity, are we saying, is it saying what we are saying that the charge controller will be able to charge this battery to full capacity within 1 hour? Is that the interpretation of this analysis? Will I be wrong if I make that? Looking at the fact that the battery capacity is a 24 amp hour capacity, and then we have done our calculations to get the solar array and then the charge controller. Let's assume this charge controller is available in the market, and we have this. Are we going to say this this installation will these batteries will be charged to full capacity within 1 hour? Or how do we bring in the time of charging into the equation?
So the time of charging will depend on the intensity, the intensity of the sun that is falling on the panels, because you can't manufacture energy from elsewhere. It's dependent on the intensity of the sun on these panels. Okay, so let me just continue.
So we worked with an assumption of a 6 hour of course hour. A peak sun hour. So yes. if we are having a peak sun hour, for example, if we are working on that same assumption of a peak sun hour, how long will this batteries take to charge?
Okay, so that's a calculation that is not considered in this case here, to determine how long it will take for that battery to be fully charged. That's what you're asking, right?
Yes, please.
Yes. It's not determined here. But what we are trying to do here is to determine the right sizing for this system and the formulas to be able to size these systems properly.
Yeah, but maybe something that if you can come back to us, because in the choice of my charge controller, the time of charging should be important. Okay.
Yeah, so that will also depend on how you're using. So, for example, the priority of the energy that is coming from the sun. So sometimes you could be using the energy and then the leftover will not be used to charge the battery. So that it varies anyway. So except you're making a certain assumption that maybe this, like you rightly said, if we assume that for a peak 6 hours peak sun hours, okay, that the sun is shining, and maybe on the assumption again that all the energy that is coming from the solar system goes to charging the battery. Okay, so based on those assumptions, we can now say calculate, okay, this is the amount of time it's going to take for this battery to be fully charged. Right?
No, you know, already for this analysis, we have assumed three additional days or something autonomy.
Days of autonomy.
Yeah. So it means that my solar panels that I have so my battery bank I have. So already I've taken that.
Look at this. Just a thought about what you just asked now. Okay, so your charge controller is rated in amps, right? At a certain voltage, maybe 12 volts, and then your batteries are rated in voltage and amp hour, right? So you need to determine. So what we are looking for here is the hour that is required to be for that battery to be fully charged. That's the question here. But I think we can just play around the formulas and then do that calculation. But let me just, I'll come back to this. I'll come back to you on this. But let me just, because it's not, I didn't create it in this slide. But now that you've asked about it, maybe I'll just add one additional slide and then put the formulas and then maybe also do 1 or 2 examples, and then the slide will now be redistributed to everyone, so that we don't spend so much time on this.
That'll be fine.
Thank you.
Okay. Thank you for raising that up. I will do that. In the first class that we had, there was this issue about connection of panels in parallel and series, which wasn't part of the slide. So I went back and I added it, and it's part of the presentation that we're making now. So when this questions comes up, we go back, then we modify the slide, we add some of this information, and then we keep updating this. That's why I say we are all co-learning in this together. So let me just go ahead. So I want to talk about penetration rates, okay? This is a situation, okay? There are 2 important parameters that needs to be kept in mind when sizing a hybrid system. So the penetration rate comes to play when you're combining 2 different sources of power, when you're having a hybrid system, okay? So for example, you're having a generator and you're having a solar panel. So one want to understand what is the level of contribution that the solar system is making in the entire energy demand. That's what we mean by penetration system, okay? So the penetration rate of solar power, okay, like I just explained now, penetration rate is the penetration rate of the solar power to the entire energy demand of the facility, okay? So energy shares in production between the solar power and the DC generation. This is just what I explained. So let me just continue. So these 2 concepts should not be mixed up. Okay, sorry, let me take this again. There are 2 concepts here. There's a penetration rate and there's an energy share. Okay, so the first one is penetration rate of solar power, and the second one is energy share. Okay, and I'm saying that these 2 concepts should not be mixed up. They are interrelated, but not the same. Penetration rates can be static or dynamic. Let me take this again because it looks a little bit confusing. Okay, there's what we call penetration rates, and there's what we call energy share. Penetration rate is for power, while energy share is for energy. Remember, I told you that energy and power are not the same thing. So when you're talking about penetration rates, you're talking about power. At every point in time, what is the contribution of solar panel, okay, to your entire energy demand? While energy share is maybe for a period of time, what amount of energy came from the sun and what amount of energy came from the grid or from the generator. That is what energy share means. It will become more clear in the slides that follows. So now this is also telling us that penetration rates can be static, it can be dynamic. Okay, so let us talk about the static penetration rate. Static penetration rate is defined as the ratio between installed PV power and diesel generator apparent power. So if you install it, for example, if your total load, I don't know if I have an example. Okay, for an example, a hybrid system with 950 kilowatt peak of PV and a total diesel generator of 1,600 kVA. This is an apparent power, which is 4 generators, 400 kVA generators times 4. This will have a static power penetration rate of 59.3 as shown below. So this is how you calculate your penetration rate. Penetration rate is equal to the PV power divided by the generator power. That is the total sum of the generator power. So when you do that calculation, you're going to have 950 kilowatt peak divided by 4 generators of 400 kVA. So when you do that, you're going to have a static penetration of 59.3. Now, this is static penetration of an installed capacity. But believe me, this will not be constant all the time. There will be a time when the solar panel will not be producing anything, and the penetration rate will be 0. Okay? And there will be a time when it will be producing 950, and then the penetration rate will be this value. 59.3. Okay. Now this is static penetration rate. For every other time when it is not producing up to this amount of time, it is referred to as dynamic penetration rate. So let me give further explanation to this. So in systems with low penetration rate, that is up to 20%, a controller is usually not needed as critical system state will not be reached, or most common load, that is for most common load. In other words, the PV output of less than 20% will always be within the limit of the base load. If you remember when I showed you the load profile of a facility, right? And I told that if you put a PV system that is below the limit or below the range of the load profile, okay, you don't need any controller to do that. You don't need any controller to manage the energy that is coming from the solar system. Okay, I was thinking I have a diagram to illustrate this, but this is a simple terminology here.
Sorry, by controller you are referring to another controller, or you are still referring to the charge controller we just discussed?
No, thank you for pointing, not the charge controller. You need a controller that senses your demand. So if you have a solar system, I have a generator, right? You need a controller to know when the generator comes on, depending on your demand. I need a controller to know when the generator goes down. You need a controller to blend the supply from the grid and from the generator. Those are what controller does for you, not the charge controller, please. Charge controller charges the battery. But in this case, we are talking about the sensor that determines what supplies your load. It's the sensor that determines the combination of the sources of electricity that can be dispatched. I don't know if that makes sense. Bear in mind that we are talking about hybrid system, meaning that you have more than one source of electricity.
Hello, Mr. Chima.
Yes, please.
Question, sir.
Okay.
If you say that a system that has less than 20% does not need a controller,
okay,
and you already have a system, maybe by reason of ignorance, the person had installed a controller, in a system, does it have automatic way of bypassing itself so the system to continue?
That controller might remain dormant because there will not be need where it has to kick in and do the control.
It will remain dormant.
Yes.
But does that play harmful? Does it play harmful back into the system?
No. I don't think so.
Additionally, does that mean there won't be a load share?
I just want to know that.
Okay. Someone is saying something additionally, what?
Yes. So does it also mean that there won't be is it still going to share the load with the diesel generator even though is less than 20%?
Now, when I say 20%, what it means that for every point in time, whatever is coming up from that solar system will be used.
Okay.
Every point in time, whatever is coming up from that solar system will go to use. So there will not be a time where you need to curtail the solar system. There will never be a time where you need all of those hybrids, the integration that you need to do. So for example, I talk about curtailing the solar system. That is, if you do a hybrid system with a generator, and depending on the structure that you give to that generator, we'll come to the hybrids and generator control systems and all of that. We'll come to that where we'll discuss, where we'll talk about the minimum loading of generators, how generators should be operated when you're running a hybrid. We'll come to that, please. Let's just continue. So in a more complex system with penetration rates above 20%, then a controller is required, is a must. So let's talk about dynamic penetration. A dynamic penetration rate is defined as the ratio of actual PV and the total load at starting point in time during operation. Okay. Now this is instantaneous. Maybe in the morning you can have a dynamic penetration of maybe 40% from the solar system. In the afternoon you can have 60%, but at night it's 0%. So it's dynamic. Okay, it's instantaneous. This is different from static penetration. Static penetration is talking about the installed capacity. Installed capacity does not mean that they are generating that capacity that they are rated at, right? So dynamic penetration is not talking about the actual generation. It's not talking about, it doesn't care about the capacity that is installed. It's talking about the actual performance, the actual generation. Compare it to the entire load that the system is delivering. So that's the difference between static and dynamic penetration rates. So here is the formula to calculate the dynamic penetration rates. Okay, so you have the actual capacity, you divide it by the actual load. In the static penetration, we are talking about the installed capacity, but in this one, we are talking about the actual capacity. So these are the differences. Okay. So other definitions are possible, and one should always check with definition. One should always check which definition is used in the specific case. So let's talk about energy share. I had introduced this earlier when I talk about penetration rate, and there's also energy share. Energy share is different. Penetration rate has to do with power, whereas energy share has to do with energy. So from an economic point of view, another parameter much more important than penetration rate is the energy share. To determine the energy share of the different types of generators, the final energy production of the PV system and the final energy production of the diesel generators are compared. So you have the diesel system, a diesel generator system, and you have a solar PV system. In the end of the day, you have to compare the energy that you've collected from the generator and compare the energy that you've collected from the solar system, and you compare them. That is what we call energy share. So you divide out of the 100% energy consumption, what percentage of it came from the solar system and what percentage came from the diesel generator. So for example, a hybrid PV diesel system produces 10 megawatts of electricity energy, and 2 of those 10 megawatts come from the PV system. Thus, the energy share of the PV system is 20%. Out of 10, only 2 came from the PV system. So if you do that division based on the formula that I didn't produce any formula for that. But if you check, if you do the percentage of 2 to 100, it's 20%, right? So that is how you determine the energy share, for any hybrid system. So compare the figures. Compare the figures. That the parameters on a sunny day and parameters on a cloudy day. Now, this is what I told you earlier. That look, energy share is determined at the end of the day or at the end of the year. You now determine how each energy source has performed. That is the solar system and the diesel system has performed. Okay. Now, what this paragraph is trying to tell us is trying to tell us about the next the diagram in the next page. Let me just go and explain that. But let me just make a brief introduction to that. So the next page is going to show us the difference between penetration rate and energy share on a sunny day and a cloudy day, with a static penetration of 40% and a solar energy system, and the solar energy system contributes an assumed 8% and 28% respectively of overall produced electrical energy. Let's just go to the diagram so we can see that. So this is the diagram that we are trying to introduce on that previous slide. So this is penetration, PV penetration versus share of energy demand. Okay, so in this case now, we have a diesel generator that is stored, that is rated 160 kilowatts. 160 kilowatts is the real power output, whereas the apparent power output is 200 kVA. So this generator is 160 kilowatts that is installed. I will have a solar PV system that is also installed, 110 kilowatts, that's the peak. Okay. So, but of course, we know that there is no way this PV system will produce 110 kilowatts at any point in time because of performance ratio. Okay, so we now assume that 80 kilowatts peak is produced, okay, of the PV at standard test condition. Okay, sorry, there's a little mix up here. This 110 kilowatt is the peak demand of the profile. Now, the PV that is installed is 80 kilowatts, but it cannot give you the 80 kilowatts. It can only give you about 60 kilowatts. Okay, and the difference is because of performance ratio. Okay, so during the afternoon when the sun is fully out, it can do 60 kilowatts. It cannot get up to 80. It can do 60 kilowatts. Now let us look at the penetration rate and then the energy ratio of these two combinations. You have a diesel generator that can do 160 kilowatts. I have a solar system that can do 80 kilowatts. Okay, but in reality, it's just about 60 kilowatts. Now, this blue section that you're seeing here is showing all the static penetration rates. Static penetration rates, okay? And static penetration rate is talking about installed capacity. So the installed capacity of the solar system is 80 kilowatts. Remember, we have 80 kilowatt installed capacity. Out of the installed capacity of the generator. Now, the generator is 200 kVA. If you remember the formula I showed you before, that is the installed capacity of the solar system divided by the installed capacity of the generator. And that's what we have here. So when you do this calculation, you're going to get 40% static penetration in this system. That is static penetration. Now let us look at dynamic penetration. Now dynamic penetration is the actual energy that is being produced. So in this case, our solar system is producing only 60 kilowatts. And the generator is can only do 110 kilowatts. Remember, our peak is 110, not 160. So that's our peak here. So your generator can only do 110 kilowatts. So dynamic penetration in this case is 55%. That is dynamic penetration. And I told you that it is instantaneous, it is time bound. So this dynamic penetration of 55% is occurring at 12 noon. The time here, this period here, it is 12 noon. And it will be different at every other time. This dynamic penetration will be different at 8 a.m. It will be different at 5 p.m. But in this example, we are only considering it at 12 noon. That's when you have this dynamic penetration here. But static penetration is static, as the name implied. It's just static. Now let us look at the energy share. The energy share is the number of these yellow boxes, these yellow squares, the number of it over the total number of all of these boxes. And that is what we have here. If you do that, you will find out that these yellow boxes represent 28% of all the energy in this profile. That's why you have 28%. And then your share from the diesel generator is 72%, which is these other gray areas. Okay. So this is your energy share, this is your static penetration rate, and this is your dynamic penetration rate. Now, this is the same thing that I did in the previous slide, but in this case, it's for a cloudy day. Imagine that the day is cloudy and there is no sun. The sun didn't come out. The penetration rate, now the static penetration rate will remain the same. Remember, it's just the same. But the dynamic penetration rate at the same time, at 12 noon, will be different. So the dynamic penetration at this time will be 20 kilowatt because that is the highest. At the 12 noon, the solar system is only producing 20 kilowatts. You then divide it by 110 kilowatt. That is the maximum peak that facility requires. When you do that, you have a dynamic penetration rate of 18%. Your energy share will also be different because the sun is not out on that day. It's a very cloudy day and the sun is not out. So if you look at the ratio of this yellow area to this gray area, you find out that this yellow area is just small. So it represents only 8%. So this is your energy share. So when somebody is telling you that, okay, we have installed a solar system, now I'm trying to make you understand the essence of this energy share and penetration rate. If somebody have told that they installed a solar system of a certain amount or certain capacity, sometimes you can tell the level of the performance of those solar systems by asking about the energy share if they have those data. So if they tell me that the energy share of their solar system is 40%, okay, and another person is telling me that the energy share of their solar system is 80% or 90%, wow, it tells you that the person that has an energy share of 80 to 90% is offsetting more carbon. So you're not burning more fossil fuel, you're not taking off on the, so you're more cleaner, you're more greener. That's what it means. Okay.
So sorry, if you can go back to that this bit. So
okay.
First, what was the energy share now? Because you are having 2% there. Is it 8% or 92%?
The energy share of solar system is 8%. The energy share is 8%.
Okay, of the solar system.
Of the solar system. So the 92% is from the generator or from the grid, but we are interested in the solar system, solar penetration rate.
Okay. Then my second question would be, is there any particular reason
your network is breaking?
You use the KVA rating for the static PA rating when we are looking at this for the generator, when we are looking at the dynamic penetration?
Sorry, can you say that again? Your network was breaking, so I couldn't hear your question.
I said when you look at it, when you are calculating the static penetration rates, you know, the generator, you gave up the rating in as 160 kilowatts or 200 kVA.
Yes.
So, so when you are looking at the calculation for the static penetration, you use the kVA rating for the generator. So yes, I was expecting it to be 80 over 160 for the unit to be the same. But when you come to the dynamic, we are using kilowatts against kilowatts.
Okay, yes. Now, this is, I understand what you're saying, okay? But we are looking at the, how do I put this? This is what the formula actually gives us. If you look at the formula I gave you, it was like that in the formula. It's in kilowatt and kVA. You can see the formula, right? So it's a standard formula that we have.
Is it? What about the dynamic?
So the dynamic. Now, this is the difference. You know, when you're talking about static, you're talking about the installed capacity. Right? So most times your generator is, capacity of a generator is rated in kVA. So that is the installed capacity of a generator. So we are using kVA because we don't know the load that is attached to it. Mind you that if you have a resistive load, your kilowatt becomes equal to your kVA. If it's your 100% pure resistive load, your kilowatt becomes equal to your kVA. So in this case, we don't know anything about the load, and that is why we are using kVA. Okay, your solar systems are rated in kilowatts, and that's why we're using the installed capacity of the kilowatts. Okay, but if you're talking about the dynamic, okay, then we are not talking about the load becomes important here, right? So if it's a pure resistive load, okay, then it's still going to be in then in that case your kilowatt becomes equal to your kVA. I don't know if that addresses this question that you raised. It's a very important observation that you made.
Yeah, thank you. Engineer Chima, I've shared the material for the other training for them, so that I actually, let me say this, I was tempted to share to all the those who registered to say, read this material ahead of time. And I think it's one of the things we'll be doing in subsequent training. We'll share some material ahead of time so that people who are not within the energy industry will know the basics, the conversion factors and everything, because kilowatt volt ampere is just the rating for generator. And the other one is, both of them are the same thing, only that this one has losses, sort of. So I've shared that material for them. So engineer, just go back to that material I shared. You will see you study further. Thank you.
Okay, thank you, Engineer. Yeah, so it's a very important question, a very important observation that you raised, and I just have to chip in that explanation. So let us look at generator minimum loading. So this is an issue for a lot of us that uses generator in our maybe factories, industries, and even in our homes. So it is important to note that every diesel generator has a certain minimum loading. It is usually expressed as a percentage of its power generation capacity, and is generally provided by the manufacturer. So sometimes if you look at the data sheet that comes, or the manual that comes with the generator, in most cases, in some of them, they will tell you that this is the minimum load, this is the minimum load that this generator should operate on. Okay, so it's important. So typically, generators should be loaded at a minimum of 30% of their rated power. This is because running an engine under a light load might lead to damage. Now, a situation could occur in which the available PV power combined with the minimum loading of the generator exceeds the current load. So in this case, there are two options to handle this situation. Let me explain this situation a bit further. Now you have a load to power. So for example, you have a load of 10 kilowatts, a load that you want to power, and you have a generator, maybe a generator of 10 kilowatt as well, should in case if there is no sunlight for your solar system. Okay, so and you're combining that generator with the solar system. So for example, you have a solar system of about 8 kilowatts. 8 kilowatts. Okay, so when that solar system is operating at its highest peak, it's producing 8 kilowatts. You're only taking 2 kilowatts from your generator. Okay, there could be a situation whereby that generator will be running at less than 30% of its rated capacity. And believe me, if you're taking the 8 kilowatts from the solar system, which is remaining only 2 kilowatts, and you're picking it from the generator, that 2 kilowatt you're taking from the generator represents 20%. So that generator is already running at below its minimum of load requirements. It becomes a problem. So what is going to happen in that situation? Okay, there are two ways to handle it. That's what this is talking about. So one of the ways to handle is that the PV inverter can be derated to produce less power than possible. So the PV will now reduce the amount of energy that is coming from your solar system and then augment it from the generator. So your generator can now operate at 30% minimum loading, and then it will take 7 or the remaining power from your solar system, just so that your generator can run efficiently. 30% is not even efficient, but just so that your generator can operate in a way that it will not cause damage to it. That is it. So alternatively, the surplus energy could be stored and utilized later when load increases or when no PV power is available. So in this case, now you're going to have a storage, you're going to have a battery, okay, to take out the excess energy and then store. So these are the two ways to handle it. But what is important here is that your generator should not run below its minimum loading capacity, which is 30%. So the second option introduces a storage into the system, making it more complex and then costly. So this is just to illustrate the generator minimum loading. So let us describe what is happening here. So the figure shows an example with a minimum loading of 30% of the maximum load of a diesel generator. That is 50 kilowatts. So 30% of, now this is from the previous diagram that we had. 30% of 160 is 50 kilowatts, okay? So a storage system is not included. So in this our example, there is no storage system that is included. Now the red color shows the cases when the PV generation generation has to be derated. Derated means that the power coming from the PV has to be rejected by the inverter. That's what it means. So now let us look at what is happening here. Now this is the load profile, the gray areas, okay? Now this is your solar system. All these gray areas are being powered by your generator, okay? So when the sun comes out by 7 a.m., now if you look at the labeling at the vertical axis, every box here is 10. So this is 10, 20, 30, 40 kilowatts. This is the unit, okay? So at this point, you're running at, this is 10, 20, 30, 40, 50. So you're running at 50 kilowatts. Until 7 o'clock, you start running at 60 kilowatts. And solar system is producing 10 kilowatts. So your generator is operating at its minimum loading capacity, which is 50. This is 1, 2, 3, 4, 5. However, when it gets to 8 o'clock, your solar system starts producing more. But because your generator is already running at its minimum load capacity, it cannot accept that further generation from the solar panel. So it has to be derated. So this red line, this red box, is the power that should have come from the solar system, but your inverter will reject it and then take that power from your generator. So your generator can maintain 50 kilowatts. So if you count the box here, you have 1, 2, 3, 4, 5. So it keeps maintaining the 50. And whatever additional generation that is coming from your solar system, your inverter will keep rejecting it. Even at 9 a.m., your solar has generated more, but your inverter has, just so that your generator will keep running at 50 kilowatt minimum load. Then if your load now increases, so at 10 o'clock, your load now increases, right? So only when your load now increases that your inverter will not allow every energy that is coming from your solar system to pass through, because then it will not take the remaining one from the generator. So by 10 a.m., the inverter is taking 1, 2, 3, 4, 5, 6. It's taking 70 kilowatts from the generator and then taking all that is coming from the solar system. So at 1 p.m., there's a drop in your demand. There's a drop in demand here, right? Bringing down the demand from the generator to go below 30%. But your inverter will not allow that to happen. So what your inverter will do, it is going to derate again your solar system, just to make sure you have 5 boxes ahead of your solar boxes. So here you have another 1, 2, 3, 4, 5. Okay, I hope this explains the concept of minimum loading for generators and then the derating strategy of inverters, how they can derate your solar system just to maintain a healthy system for your generator. So this is just basically talking about a hybrid system and how the controls, are being programmed to operate.
Thank you, Yashima. If I can ask, so is the inverters designed to do this, or are they supposed to be a controller?
I get your question. I get your question. So some inverters have these capabilities. We are beginning to, technology is beginning to evolve so fast. So we have some inverters with these capabilities, whereas you can also have a separate controller that does this. There are separate controllers that can do this. It's just a question of programming and then, and all of that. So some inverters has these capabilities, whereas some you need a separate controller to do it. If there's an SFA inverter, it's a German technology. It's very popular in Nigeria. It has some of these functionalities. You can blend supplies from the grid and from your generator and from other sources. So the technology is there.
Mr. Chima, can I have a question?
Okay.
What you have just explained now, what's different between this one and the load management system?
And load management system is generic.
In a typical system.
Load management is generic. You can do load management in so many aspects. Okay, but this is also part of load management. This is part of load management, but it's in this case it is automatic. You have given the command. You have told the machine what to do at every point in time. So it's part of the load management. So let us look at different setup. Now this is the categories of the PV diesel hybrid system. Okay. PV diesel hybrid system. So you're combining diesel generator and you're combined with solar system. So if you move from this point where you have a complete diesel, 100% diesel system, okay, In this case, you just have diesel. I mean, diesel generator. There is no PV system. Okay. If you move from that point to the right side of this diagram, where you have 100% PV system, in this case, you have completely eliminated diesel generator. Now, what you will notice that as you keep moving, you keep increasing the solar panels that is required, and you keep increasing the batteries. So for you to completely eliminate your generator, you will need a heavy battery storage system. And that's cost a lot of money. And these batteries will not last forever. Okay. Best quality battery and well maintained. I mean, best quality of them, maybe 10 years. Yes, maybe. Okay. I'm talking about lithium ion batteries. Maybe 10 years. If you're talking about lead acid battery, maybe 6. I mean, well maintained. Okay. But in most cases, people don't give so much attention to the health of these batteries. You don't pay attention to the depth of discharge and the temperature, and there are a lot of things that affect the life cycle of these batteries. Okay, so and they don't come cheap; they are very expensive. So if you want to do away with generator, you have to, you know, your battery pack has to be large, you know, to take care of any load that you have to put in at night and all of that, up until the sun comes up again to charge your system. Okay. So this literature just to explain what I've just said now. So let me just move ahead. So let us look at the different setup. In a 100% diesel system, fuel consumption and emission are at maximum. Of course, when you're doing 100% diesel, okay, you have to deal with high fuel consumption, and of course, with the impact of climate change and all of that, you have emissions, and then all of these are at maximum. It is a simple solution for off-grid electrification with no disadvantages, and the disadvantage is high fuel cost and high maintenance cost. Okay. So with the connection of small PV system, the diesel generator is supplemented and fuel can be saved. The PV system is then connected directly via an inverter to the diesel grid. That is the grid that connects the diesel generator and the solar PV system. So for larger PV systems with static penetration rate between roughly 20 to 60%, controllers has to be integrated. I've said this before, if you're dealing less than 20%, you necessarily don't need a controller, because whatever is coming up from the solar system can be absorbed. But if it's going above 20%, okay, you might need a controller, because sometimes you might need to combine the amount of energy that is coming from the solar system and from the generator. You need to give them an instruction on how to manage their conflict and all of that. And that's where controller comes in, to settle their conflict and then make sure that everyone is happy. So again, the penetration rate is not equal to the fuel saving. So if somebody tells you that I have a solar system and I'm getting a penetration rate of maybe 60%, it does not, and of course you're running a diesel generator for the remaining 40%. It does not mean that that 60% is the fuel that they're saving, okay, that they ought to have used when they're running that generator for 100%. Okay, so fuel savings for setups with up to 60% static penetration rates, static penetration ratio, are usually around 20 to 25%. Now, I said this before, that when your generator is running on a higher load factor, it burns more fuel. When it's running on a low load factor, it burns less fuel. Okay, so that is the idea. The idea is that your generator, when you have a hybrid system and your generator is running at a low load factor, then you burn less fuel, and then you save from that less fuel that you're burning. So a higher static penetration rate and thus higher PV energy shares can only be raised by integrating storage into the system. Since there are still no other grid forming devices beside generator, at least one generator still has to run all the time. I will explain this further as we go in this presentation. So if we push the solar energy share to 100%, all energy demand is covered by the solar system, and no diesel generator is required. This is the question that one of the participants was asking the other time. So now this is the downside of it. However, However, please note that reaching 100% leads to a disproportionate increase of the system size. This is what I tried to explain to her that time. If you want to cover all your load 100% by solar system, it will lead to a disproportionate increase of the system size. Now, this happens because we have to cover the entire volatility of the solar resources with more solar panels and especially more storage. Therefore, in large systems, it is usually more economical to keep a generator in the system as a backup source for period of low irradiation. Now, when you're talking about generation sources or power supply sources, there's what we call dispatchable generators and non-dispatchable generators. Your solar system is non-dispatchable. You cannot call your solar system at any time and it will answer. But your diesel generator, you can call it at any time, it will pick up. If there is no sun and your battery is drained and you need power, your solar system cannot answer you. So it's non-dispatchable. But your generator system, just add fuel and you kick it at any time, it answers you, right? So these are the reasons why it is important to have generator. Even for people that does mini grid these days, you do your mini grid, you have your battery system. In many cases, you still have to have generator. Okay, so that's the situation that we have in Nigeria.
Chima, can I ask a question?
Go ahead, please.
As you begin to explain this thing, my mind is agitated because I know that there's a general concept that the world is going green, and invariably the fossil fuel. So when you explain all these things, it tells me that the generator is here to stay forever.
No.
So which means that concept of green is a hype concept that might not really come to see the light of day.
No, thank you very much. It's because of the peculiar situation in Nigeria. It is not a global trend. And it is happening because we don't have a reliable grid. If you have a reliable grid, right, then you don't need generator. It is just because of the peculiar situation of Nigeria. If you're in Germany, now let me tell you what Germany does. Germany has a reliable grid. In Germany, when you're doing solar system in your house, you don't need battery. You just connect your panels and you connect it to the grid. They do net metering.
Smart grid. Smart grid.
They have a smart grid. So during the day, when you're out, when you've gone to work, your solar panel is generating all the energy it can generate and it's sending it to the grid. And at that time, the industries are working. The industries are picking up this power and they're using it. When you come back at night, you not collect at night, they will not fire maybe their coal or their gas power plants, and they will supply you back that energy. So at the end of the month, they now do a net metering. Who has collected more? This is the concept I explained yesterday. Okay, go ahead.
Maybe the net metering thing, you might explain it. Let me say in a layman's language. Your meter will be reading negative.
Yes.
Your meter will be reading negative. You know, if you load 100 units, 100 units will be loading 94, 99, 98, 94. In Germany, when your capacity have fully charged, your solar is on, and your consumption is not optimal, your meter will start reading from 90 to go to 91, 92, you are gaining. So that is what smart metering, smart grid does. So like Chima said, it's a peculiarity of Nigeria. And meanwhile, when we're also saying this, remember that the generator must necessarily not be fossil fuel. It can also run on another renewable energy source. But that is still being, that's not yet the case in Nigeria. Thank you.
Okay, so thank you for also bringing that up. Thank you, Generation. So now let us look at adding storage, okay? So energy storage incorporated in a PV diesel hybrid system can have several functions or purposes. Most commonly, a storage system is used to do the following. It is used to control the power quality. So in terms of the voltage, you can use to stabilize the voltage, the frequency, the reactive power, and all of that. You can also use it to provide additional spinning reserve, okay? You can also use it to avoid derating. Remember, I explained the concept of derating of a PV system. So you can use storage system to avoid derating of your PV output by shifting produced solar energy to later hours of use, right? You can also use it to reduce your maximum loading of generator. You want to do peak shaving, okay? You can use batteries to achieve all of that. So all of these are the reasons why you add battery storage. Okay, so a storage unit has to be able to provide electric power within seconds. It should have a high cycle efficiency and a low self-discharge rate. So the following table will give a brief overview of some available storage technologies used in the PV diesel hybrid system. So these are some of the batteries that are in the market. So we have the lead acid battery, we have the lithium ion battery, we have the redox flow. Okay, so these are the properties. I told you that lead acid battery has a DOD of 50%, and if you're using lithium ion, it can even be up to 90%, depending on the type of lithium ion that you have. And then this is redox flow. Now this is even 100%. Okay, but they have their pros and they have their cons. So the advantages and disadvantages. Okay, so the advantage of lead acid battery that it has a proven track record. Okay, it's highly available and it is also highly modular. Whereas for lithium ion, it has high energy density. That's the advantage. Okay, it is low weight. It has a low self-discharge. Okay, these are the two very common in the market, and there are some other new technologies that are already coming up now. They have their disadvantages as well. The disadvantage of lead acid is that it has a low energy density, right? It has a light weight, and it is frequent maintenance for liquid type. That is, there are different kinds of lead acid batteries. So for the liquid types, you need to do a frequent maintenance on them. Then for the lithium ion batteries, it is expensive. Yes, we know it is expensive, but it has a higher DOD and a higher lifespan as well. So it no long-term field experience that is required. It does not require. Okay, no. What is this saying that we don't have a long-term field experience in lithium ion batteries? Okay, but I believe at the time this information was compiled, because I know for now, I mean, the experience is there now, but maybe not long enough to compare to lead acid, because lead acid has been there, I mean, for a very long time. Okay, so this could be the disadvantage, because not a lot of people has a good knowledge of lithium ion battery, even though it does not require so much maintenance, but it also needs to be properly cared for in terms of the operating temperatures, monitoring the DOD, and so many other things that are required. So this is just a picture of an example of a battery pack. So let us do a simple simulation of a PV diesel hybrid system. Okay, we'll conclude this.
Excuse sir.
Okay.
Hello.
Okay. Yes.
Hello.
I'm hearing you.
What is that? What is that capex? The former slide. Yes.
This capital expenditure. Capex means capital expenditure.
Capex.
Yeah, it's difficult for me to hear you, but I believe you're asking about the capex, where you have the low capex, medium, and high capex. Is that what you're saying? Your network is
okay.
Yes, that's what I mean. This is low capital expenditure. This is medium capital expenditure, and this is high capital expenditure. Okay.
Engineer Uche. Hello, engineer.
I can hear you, sir.
Okay, just wanted to ask a quick question.
Yes, sir.
Yeah, in the battery types, you showed the lead acid and lithium ion. Don't we use NiCad batteries, nickel cadmium?
Good question.
Okay, go ahead.
Go ahead. No, go ahead. Go ahead. Go ahead.
Okay. So this application, that's in this application.
Yeah. So there's no way we can cover all the whole battery technology in the market.
No.
So these are the
I understand. I just wanted to ask.
Okay.
Let me also say this. Also you look in terms of usage. These are the batteries type that have future, especially lithium. A lot of research is being done now in Europe as regards, but yesterday we talked about large scale storage is a major challenge, but Tesla have been doing a lot of work on it, and they are leaning towards lithium ion. So that nickel cadmium,
lithium ion is okay.
Okay.
I mean, lithium ion is okay, but
size is a problem. There is no.
Yeah, whatever it is. My own question is, if we can have lead acid, I do not know why we cannot have an example of saying nickel cadmium, because lead acid is just as old as anything you can think of, and in most applications. So that's why I'm asking if in solar applications it is not used. In most applications, nickel cadmium is what is being the preferred choice, like in UPSs and other industrial inverter systems that I had worked with. That's what I see. But of course, they are not connected to solar. So that's why I was asking this question.
Yes, your question is valid. Perhaps because of the small nature of those applications, maybe those kind of technology is suitable. But when you're talking about a large-scale installations and all of that, I think the cost now begins to weigh in, and then you begin to go for these technologies that has been there for a long time, and that the cost has really come down to a certain level. So which goes back to lead acid or lithium ion and all of that. For mini grid developers and for large scale applications, I mean, it's the most popular batteries among them are just lithium ion and then lead acid. So, but of course, there are other different battery technologies. Some are still coming up because it's an area that a lot of people are still experimenting. We've not achieved a major breakthrough in storage technology, and that's why we're still having a little challenge in terms of the renewable energy space, especially for developing countries like Nigeria, where we don't have a stable grid. Okay, if we achieve a major breakthrough in the battery technology, it's going to go a very long way in the use of renewable energy in countries like Nigeria.
Chima, I also read something some time ago where they postulated that nickel cadmium batteries are very high, they are very expensive, and that their maintenance is also difficult, and that the inverter chargers are difficult to configure. So for people to lean towards these known batteries that you've mentioned, there definitely there's a reason for that. So the cost is high, and we all know that when you are doing projects, cost is a major factor. So for me, I know that lead acid battery are still the cheapest in the market, but research is going on towards lithium ion, and that's why 90% of the battery we use now in our phones are lithium ion. That means that's where the research is going. That's where the trend is going. It's just the large scale application now that need to be optimized. Thank you.
Okay, thank you, Engineer Oshe. Let me just proceed. I want to talk about dynamic system behavior. So I'm going to walk us through a load profile and then how a hybrid system that is connected to a certain facility. We have the load profile of the facility. So we're going to track the facility from round the clock, 24 hours, and see how the generator and the solar system, how they interact with each other to deliver the optimum energy system. At some point, there will be derating. At some point, a certain number of generators will be running and all of that. So let us just walk through it. Okay. So in this example, the system has the following. In our example, PV nominal capacity is 1,200 kilowatt peak. Four diesel generators are in place, each with a maximum power output of 320 kilowatts, each of them. So if you times 4 times 3, you're going to get 1,280 kilowatts. That is the capacity of the generator in terms of real power, kilowatts. Okay. So here is the technical requirements of the system that we're considering. Spinning reserve of the genset must be greater than 5%. Now, let me explain what spinning reserve is, because I know I will not explain it in any of our presentation. And I think this is the second time it's coming up. When you're running your generator, your home generator, if you're running your, let me use, I pass my neighbor, your Tiger generator, okay? It is expected that you don't load that generator 100%. If the generator is 1 kilo kVA, your Tiger generator, it is not expected that you load that generator up to 1 kVA. You should reserve some little capacity. Should, in case if there's a fluctuation, maybe you're running your fridge and your fridge comes off and then peak. I mean, you need to have, now in essence, you need to have a little bit of tolerance. That's what spinning reserve means. So should, in case if there's any additional load that quickly comes up, then your generator will don't have to shut down. It should accommodate it. But this additional load has to be kind of a transient load. Otherwise, you need additional generator capacity to keep them running. Okay. So spinning reserve is just trying to create that allowance. Should, in case if any sudden load comes up, that generator should be able to accommodate it without shutting down the entire facility or knocking down the generator. That's what spinning reserve does. Okay. So we're talking about battery. You will have heard that battery can be used to serve as a spinning reserve. So you can have battery capacity, by the side, so that if there's any sudden load that comes up, the battery can supply that load. Okay, instead of knocking off your generator, the extra energy that is required to power that load will now come from your battery to power the load. That's what essentially what spinning reserve is all about. So in our case, we must maintain a spinning reserve that is greater than 5%. Okay, minimum operational load per genset is 30%. The generator cannot operate below 30% of rated power. Then at least 2 generators must run in times of load greater than 320 kilowatts. Mind you that one generator is 320 kilowatts. But anytime the load exceeds 320 kilowatts, then 2 generators must run. And the reason is this. I talked about dispatchable and non-dispatchable generators. Solar system is non-dispatchable, meaning that you cannot call it, it can disappoint, it can fail. Okay, let me not use fail so that some people will not begin to think that, oh, solar systems can fail at some point. No, that is not. So the solar system is not 100% reliable. That is the right word. It's not 100% reliable unless you have massive amount of battery storage. But if you want to optimize cost, then you don't need to put large amount of battery storage because it will make the whole project financially inviable. Okay. So in this case, we want to deal with battery. We are not dealing with battery. So we're just having diesel generator and a solar system. That's what we have here. Okay. So there is no storage and there is no grid connection in this our example. I wanted to make it simple because if you add grid connection and storage, it's become more complex because you need more programming on your controller to handle all of that. So let us just deal with generator and the solar system. So this is our load profile. The gray area and the dotted line. This is our load profile. Now this is PV generation profile. This other portion is the PV generation profile. Here you have generator 1. These are generators. This is generator 1, generator 2, 3, 4. Now this is the total generator. I mean, total output from the generator. That is this bar that you're seeing here. And this bar is the bar for PV, actual output of the PV system. That's what this bar does. Okay. Now this bar shows us the penetration rates. Okay, and then this place shows us the actual load. So if it is maybe, for example, 100 kilowatts, it will show us if it will show us 100 kilowatts here. Then this bar will now show us how many is coming from the solar system and how many is coming from the generator. That's what this bar does. Okay, so I think I've explained this place. Let's check the next place. So now let us start. Now look at here. This is 1 a.m. This is 1 a.m. here. We are at 1 a.m. That's at night. There is no sun available. Thus, the diesel generator provides all necessary power to the load, which is 559.3 kilowatts. That is it here. This is the total power. 559.3, and all of them is coming from generator. That's why 100% gray. They're all coming from generator. So the three generators operate at 186.4 kilowatt each, which is 58% of the rated capacity of the generator. So you have 3 generators running, okay, to be able to meet this load of 559. Is shared among these 3 generators, and they are all operating at 58% of their rated capacity. That's what is happening here. So let us go to 2 a.m. So at 2 a.m., the load is slightly decreasing. So the generators also reduce their electricity output to 178.3 kilowatt each, which now correspond to 56% of the rated 56% of the rated power. Now, the TV set point is not relevant at night. It will be explained later, yes, because there's no sun, obviously. So now, this is 3 a.m., okay? So now we see that just after 2 a.m., the 3rd generator was switched off, and the 2 other diesel generators had to increase their power output in order to cover demand. Now they produce now 258.5 kilowatts, which is 81%. Previously they were running at 58. This is the load profile. Note that it is coming down, right? It is coming down. So they were running at 58 and they suddenly came down to 56, but now it has also come down further to the point whereby 2 generators can conveniently support the load. So 1 generator goes off and then transfer its load to the other 2 generators. That's what essentially happened. So when it transfers the load to other 2 generators, their load factor just jump up to 81, okay? So which is now their load factor is 81% of their rated power. So at such a low load, 2 generators are sufficient to supply power plus spinning reserve. Spinning reserve can be seen as the buffer. I've already explained this. It is the power generation capacity of a diesel gen set in operation, which is currently not used. Moreover, the efficiency of the diesel gen set increases with its load. So the more you load the diesel generator, the more it improves its efficiency. So switching from 3 to 2 generator sets saves 4. Okay, so that's what's actually happening. So at this point, it's still 100% generator. So let's look at the next line. So now this is 4 a.m. So the rest of the night, the 2 diesel generators, Gen 1 and Gen 2, supply the electricity. The load does not fluctuate in the simulation, does. The diesel gen set can operate in a stable manner. So this is, we're here now, this is 4 a.m. Okay, so the load is still declining, it's still reducing. So the 2 diesel generators can confidently handle it. So they have reduced from 81% to 79%. At this time, it is still 100% diesel generator. So now this is 4 a.m. again, I think, yeah. Okay, so this is just similar to the last. Okay, this is the same 4 a.m. Now this is 6 a.m. I think this should be 5 a.m. There's a mistake here. This should be 5 a.m. But this is 6 a.m. So at 6 a.m. now the sun is rising and the TV system starts to generate electricity. Its current feed-in is 24.3 kilowatts. Look at it here. This little yellow area is the sun coming out. Okay. And at this time, it is generating 24.3 kilowatts. Now, the diesel generator could therefore reduce their power output. Which can you please move every other person, please? Okay, thank you. So the diesel generator could therefore reduce their power output slightly since part of the load is covered from the PV system. So any energy that is coming out from the solar system is being absorbed by the load, and it's now relieved the generator, of that amount of energy. That's what's happening here at 6 a.m. So you can now see that 5% of the total load now is coming from the solar system. 95% is still coming from the diesel generator. So here the penetration rate is 5% at this point now. So let's see what happens by 7 a.m. So now this is 7 a.m. So at 7 a.m. the PV system generates 160.5 kilowatt, which is 13%. So now the penetration rate has increased. As the sun is coming out, the penetration rate is also going up. Okay. So now the penetration rate is at 13% of the nominal capacity. Now the penetration rate now is at 1%, not 13%. It is the okay. So I take this again. The PV system is now generating 160.5 kilowatts, which is 13% of its nominal capacity. And the penetration rate at this time is 31%, which means from 525.4 kilowatt of total load. So the total load at this time is 525.4. Look at it, it's written here. That is the total load. And you can see the penetration rate of this PV system. It is 31, whereas 69 is coming from the diesel generator. That's just what simply this is talking about. So let us keep going and they see how the generator keeps. Now, as the sun keep rising, it keep reducing the energy share, or not energy share, the load factor of the generator. Now the generators are operating at 33%. Very soon now they will get to the minimum loading factor. Now you can see that this penetration rate of the solar system has now increased up to 63%. Okay, whereas the generator is only giving out 37% at this time, right? Now, one will begin to wonder, why do we need to run 2 generators here? Because if you combine these two, you're still going to get 66%. Why do we need to run 2 generators? Okay, now the reason is this. Remember, I keep saying about reliability, dispatchable and non-dispatchable generator or power source. Okay, because the solar system can the reliability of the solar system can decline at any time. So, for example, a shadow might pass through the solar panels, and the intensity of the sun will be blocked, and the energy that is coming from that panel will drop, unexpectedly. So when that happens, you need a generator that can pick up that power immediately. You don't have any seconds to begin to on the generator. The generator has to keep running to pick up that power immediately. And that's why you need to keep running these 2 generators to make sure you cover this total energy that is needed. If you're running 1 generator, which is 320 kilowatts, well, you need to support a load of 569, right? So what happens if this solar system, if there's a shadow on this solar system and it declined unexpectedly, you don't have any time to begin to call off the second generator. So that second generator must be running to cover up this capacity. Should in case of if there is a shadow on this solar system, your load can still be maintained at 100% reliability. That is why you need to keep running these 2 generators. Now at 8:30 a.m., just after 8 o'clock in the morning, a special situation occurred. The power output from the system had to be limited below its actual power output potential. This was necessary because the power output from the 2 operating diesel generators was already reduced to their minimum load level of 30% of their rated power. It could not be reduced any further. Since excess electricity cannot be stored in this system, the PV power output had to be adjusted according to the load level. Now, this is what happened. Now, remember that as the sun is rising, it's reducing the energy demand from the generator. Now, the generator has gotten to their minimum loading, so it cannot go further. And the sun is still coming out. So what happened? The only thing that can happen at this time is that the energy from the sun has to be derated. Okay, it has to be reduced so that this generator can keep running at their minimum load. So any other energy that is coming up from this solar system will be derated. That is the situation here. And controllers does that. Okay, this is has been programmed so that they can run automatically on autopilot. Then while you focus on your, maybe if for example, if it's a factory or an industry, you focus on your business, and this can just, you know, automatically work on their own, and then make sure you have reliability in your power supply. So now let us see what is actually also happening here. Now the demand has also increased. Okay. Now what you're going to see is that the third generator has come up. Look at it here. Then the third generator was switched on at 9 a.m. The third generator was switched on. Somebody might begin to ask that this does not make sense. You have two generators that is running at their minimum load, and you're adding another generator again, and it's also running at minimum load, and you're now derating the power from the solar system. Okay, it doesn't make sense. I mean, if you look at it from that perspective. Now look at the reason why your third generator has to come up. Because your demand has increased. This is your demand. It's because it's daytime now, and your more load are beginning to come up, and your demand is beginning to rise. Okay, the more your demand is beginning to rise, you must have adequate generator capacity running that can cover up your total load, and that's why the third generator has to come, because this you're not having 625.7 kilowatts as a load. If you're running only two generators, remember you must have 5% spinning reserve, greater than 5%. So if you add your spinning reserve of more than 5% plus these two capacity, it will be less than 525. So you need a third generator to come up to cover up this. Generators are running at their low load. They're running at a low load factor. So their fuel consumption is not so much. Their fuel consumption is not so much. So you're still saving energy in terms of reduced fuel consumption, even though you have 3 generators running. And you know the major cost of generators are the fuel. You have to keep buying fuel and stuff like that. So your fuel consumption is reduced at this time. So now this is 10 a.m. The situation continues. The generators keep running, 3 generators keep running at 30% load factor. Whatever that is coming up from your solar system is derated, obviously, just to maintain the health of your generators. And the situation continues. Your generator keep on running at 30%. And what happened now? Whatever additional demand, because your load keeps on increasing. So for whatever additional load that is needed will be picked up from your solar system. So let's look at before now. This was 58%, right? So now the load is increasing. It now pick up again at 60%. Okay, now it has increased to 63%. You're still running 3 generators, but whatever additional energy demand that is required is coming from your solar system. So your penetration rate keeps on increasing at 63%. Even though your solar system could produce almost all the energy that is required for this entire system, because okay, let us look at this is the solar system profile. Okay, you can find out that you can see that it is greater than the load demand. But however, you cannot take everything. You can't take it all. If you take everything and then shut off your generator, if there's any problem on this solar system, your entire system will just collapse. So you don't want that. So that's why you have to keep a backup generator to keep running, and then you have to derate whatever is coming from your solar system. Okay. So the sun keeps rising, you keep having increasing load, and then your penetration rate keeps on increasing to 64% this time. So now something happens. Let us read. So at 2 p.m., the PV power output suddenly drops sharply for a few minutes, only producing half of the power as before. Thanks to the spinning reserve of the diesel generators, they can increase their power output immediately up to 189.3 kilowatts each. So that demand now is representing 59% for each of the generator of their rated power. So in order to ensure the supply of that, this generator came up to carry the load that the solar system has dropped, just to ensure the reliability of supply for the industry that they are powering. So the reason of the drop in PV power output could be a passing cloud or other shading effect, okay, that could have caused it. So now let us see what happened. So these generators we are running at 30%, their minimum loading, but all of a sudden there was a shadow on this solar system, and its energy production dropped significantly. So this generator quickly absorbed the energy, the power that it has shaded, that this solar system has dropped. They quickly pick it up, and their load factor now increased to 59%. You see the importance of having a backup generator in a situation where you don't have a storage. Assuming you have a storage, maybe storage can come in and serve this purpose. But in our simulation, we assume there's no storage. Okay, you could run this simulation in so many dimensions. You could have a storage and then try to understand how it behaves, and then understand to. I think you can design your own control system and then speak to a manufacturer to program it for you. So you speak to a manufacturer, you tell them, this is how I want the system to behave, and they will program it for you, and you have it up and running, okay? Or you can also pick off the shelf solution. You go to the market and pick controllers that are already in the market, and then you pick them and you deploy them to your system. So it can be in two ways. You can do a customized controller. You can buy off the shelf controller. Some of them are already embedded in this in the inverters that you can deploy. So all of these are just evolving technologies. Maybe years down the line, they were, before now, they were not existing. But all of these are coming up as a result of innovation to optimize the solar system. So at 3.
Question.
Does someone have a question?
Yes, please. I actually want to find out, you mentioned something about the controller. Does the controller also send the load demand so that when there's a higher load demand, then the generator will now pick up the load?
Yes, that is what the controller actually senses. It senses the demand, and it now controls the supply sources depending on how you want it to behave, depending on the kind of command that you have given to it. Okay, so it senses the demand, and then it mixes the supply sources to meet that demand.
Sorry, if I may ask. So looking at the us running 3 generators, yeah. So I'm assuming they have to be on the same bus and they have to be synchronized.
Yes.
So are we also bringing the source of the inverter now into the same bus for the controller to be able to pull these things together? So are we more like synchronizing the inverter with the generator sources?
No, it depends. This depends on the controllers that you're using. Some inverters have these controllers inbuilt in them. Like, so if you meet original equipment manufacturers, they can do they can build a customized solution for you, or there are controllers that you can pick, and then also you have to look at their wiring system and how they communicate. Okay, so I don't think there's a generic, there's a one-size-fits-all for all of this, but there has to be that synergy between the generators and then the inverter.
Thank you.
Okay.
Hello, sir. Hello.
Hello.
Yes, sir. Is there any condition that you make a diesel generator or the grid non-compatible with PVC? I mean, the solar power generation.
So if you need to synchronize different power sources, okay, you need to harmonize the power quality has to be harmonized. And all of those.
Okay.
Yes.
There is a special special equipment to harmonize them.
Of course, if you're having a hybrid system, those are the special features that they have.
Because like in power generation, when power is coming from different distance, we have synchronoscope that will check the voltage, current at each one before.
Exactly. So that's what I'm saying. So if you have it, that's the special feature that hybrid inverters have. They have those characteristics. Yes, to be able to do that.
Okay.
Okay. So thank you. So let us continue. So now, what happens?
Just before you continue.
Okay.
Is it okay if I just taking it from the last speaker's question? Okay. Is it okay if I liken the controller that you are talking about to, say, a power management system that affects load sharing function on generation systems, or systems where you have grid supply as well as own generation, and you share the load between the different sources? Is it something like that with the controller?
I'm trying to understand your question. Can you say that again?
Well, he mentioned in power generation. Now, if you have a set of generators, different generators, if I take turbine generators, you would want to share the load. Of course, you balance them, and you leave some with the spinning reserve just for eventualities. So that sharing of the load is performed by a power management system. It's a computer that does that. It shares the load for you. So
controller is a computer.
That's what it does. That is what it does. And if you take, say, the national grid, you have different sources. You have the hydro, you have the thermal stations, you have the gas turbines. And we all know that the hydro stations take up the base load. But when you have the peak loads and during high demand, that's when the thermal stations now become the game changers. Without them, your system, the whole grid will collapse. So they come in immediately because of their fast response. They are able to move in and take up any additional load. Yeah, so that's what I'm trying to say. So the controller is like something like that. It can be small, depending upon the aggregation of your system.
Yes.
Okay.
Yes. That is, so the same thing is the same depending on the how you want it to function. But that's basically the function of a controller.
Okay, thank you.
So this is 4 p.m. 4 p.m. now. The load is now beginning to reduce. Okay. So as the load begins to reduce, you will see that you will notice that the penetration rates of the solar PV will begin to reduce as well. Okay, because the generators are already running at their minimum load. Okay. So you can see the generators, now that the sun is declining, okay, is declining. The solar system is no longer derated at this time. So the generator is beginning to take over from the solar system because the sun is now beginning to go down and the generator is now beginning to take the excess load. So they've moved now from their minimum loading. They've started increasing because the sun has started going down. Okay. So now this is 6 p.m. The sun is almost going down. It's now at 15%, and the three generators are now running at 72% of their rated power, their 70% load factor. So now the solar system has gone down significantly, and the fourth generator comes up. The fourth generator came up so that together, if you combine the four of the capacity, they should be able to meet this load demand. So the fourth generator came up so that they can support this load. The solar system is almost gone. It's now 3%. And then if you notice, we have 811, and then it's now dropped to 708 something. So the fourth generator quickly went off again because this three generator can handle that. Okay, so he went off and then transferred its load back to this three generator, and it is 100% generator now. Okay, so all of this is what a controller does. So you can now see that the load is now beginning to reduce again, and the capacity of these generators are reducing. You see, the load is still going down, and the capacity of the generator keeps going down, and all of that. Okay. So I think this is the final slide to this. Okay. Now the essence of this is just for us to have a clear understanding of what a controller does and how you can actually design your own hybrid system, optimize it, and then look for a controller or an inverter in the market that can help you achieve that objective. Or you can even talk to original equipment manufacturers and then see how they can program a controller for you and all of that. All of this is possible, but the key thing is make sure that your system is well optimized. The system that we look at now does not have storage. It's just only diesel and then PV system. Okay, you could have storage in your own case. You could also connect to the grid, but I don't want it to be too complex. That's why I just use hybrid generator system. Okay, so
sorry, question, sir.
Go ahead. Okay.
Just one question. So from the look of things now, we can conveniently say that the controller will always be necessary when we need to switch load between generator and PV. That's what I can see over and above all that we have said, how to switch load between generator and PV. So in the essence, where you don't have a battery bank, so which means you don't really need a controller.
Yes. I don't understand your question. You say when you don't have a battery bank. Now the long and short, if you're combining two different sources of supply, and that's those sources of supply, okay, one of them is exceeding 20%. So if you're introducing a solar system and it exceeds 20, now the 20% is assumed to be your base load. That's the assumption.
No, so okay, sorry. I think let me put the question this way. Hello?
I'm hearing you.
Okay. What I'm actually trying to say is that maybe when you have an inverter system that runs both day and night, and you don't need a generator. Most times we find a situation like that. How does this work?
Okay, so in that case, it's not a hybrid system.
And does the controller?
It's not a hybrid system. Controller comes in when you have a hybrid system. This is a pure PV system that you're talking about.
Some people use inverter. They don't even use